How do tiny grains of dust in a protoplanetary disk grow into massive worlds? What hidden tipping point transforms an icy core into a runaway gas giant? Why did some of our solar system's outer planets become colossal gas giants, while others remained smaller ice giants? In the darkness of a newborn star system, a gentle cloud of gas and dust swirls in silence. It forms a broad, flat disk encircling a young star, glowing faintly with the light it reflects. This disk is like a vast cosmic sea of debris, thin and ethereal, yet spanning tremendous distances around the star. In its midst, the infant star flickers and flares, but out in the disk's far reaches, all is calm and still. This is a protoplanetary disk, a celestial cradle where new worlds begin. Within this wide, delicate band of material, countless dust grains drift and occasionally collide softly, sticking together bit by bit. Their surfaces carry a slight electrical charge and a coating of frost, helping them cling when they touch. Over countless years, these tiny specks gather into clumps and clumps into boulders. Nothing moves quickly here. Each encounter is subtle and slow. The growth is gradual and quiet, a tender accumulation guided by gravity's gentle hand and the sticky embrace of ice. Far from the bright warmth of the young sun, the environment within the disk is cold and still. Ice crystals coat the dust grains beyond a certain distance from the center, a boundary known as the frost line. Here, water and other gases freeze solid onto the drifting particles, adding mass to the building blocks of future giants. In this distant zone of twilight, material can amass in ways impossible closer to the star. The entire disk is turning, though one might barely notice the motion on a human timescale. A dust grain in the outer part of the disk might take decades to complete a single orbit around the newborn star. In this expansive, cold ring, time stretches out and change comes slowly, setting the stage for the quiet birth of worlds. This outer region of the disk becomes the womb of the gas giants, quiet, frigid, and ripe for creation. Amidst the dim starlight, larger bodies start to emerge from the haze of the disk. Tiny pebbles merge into rocks, and rocks merge into mountain-sized chunks as the gentle collisions continue. As these embryonic masses grow, their gravity strengthens, pulling in more and more material from their surroundings. Imagine drifting through this primordial nebula. You would see ghostly clumps of dust and ice gradually coalescing, their forms silhouetted against the faint glow of the distant star. Here and there, one of these nascent worlds grows large enough to become roughly spherical, held together by its own developing gravity. Each new protoplanet orbits the infant sun along the disk's plane, following the gentle curve of that cosmic path. They are sparse and scattered at first, far apart in the vastness, like lone islands in a dark sea. Yet gradually, some gather enough mass to attract not just solid debris, but the surrounding gas as well. In these cold outskirts, one particularly ambitious clump of matter begins to stand out among its peers. It has grown massive on a steady diet of frozen water and rocky minerals, swelling into a substantial proto-world. Its surface may still be a frozen, rugged terrain of ice and rock, but its influence now extends beyond its solid core. This young giant-to-be is becoming a focal point, and the gas in the disk around it starts to heed its call. On rare occasions, two of these budding worlds might drift into each other. Such a collision, occurring in slow motion by human standards, could shatter them into pieces, only for gravity to gather the debris again into a new, larger body. But for the most part, the big get bigger. The larger a protoplanet grows, the more strongly it pulls in the remaining material around it, snowballing in size. This growing world-to-be feeds patiently on the materials around it. Swirling gas and dust begin to respond to its gravitational call, spiraling inward towards the nascent planet. A delicate dance ensues as the forming giant clears a broad path in the disk along its orbital track. Within this cocoon of nebula gas, the young planet steadily collects matter, grain by grain, gas molecule by gas molecule. There is no hurry in this cosmic cradle. Millions of years slip by in silence as the protoplanet gradually gains bulk. At first, it may have only a tenuous halo of gas clinging to its icy surface, too thin to be called an atmosphere. But as more material falls in, that halo thickens. Tiny icy pebbles and dust rain down onto the growing world. As they descend through the emerging atmosphere, some of their ice coating vaporizes, adding a whisper of water vapor to the mix. Clouds begin to form from this moisture, and occasional droplets condense and fall. The first gentle rains on a world that has never known liquid water before. Deep below, on the surface of the accumulating core, these rains might briefly collect into cold puddles or a shallow ocean, only to freeze again as the heat dissipates. All the while, the planet's solid core continues to grow, and above it, an atmosphere is slowly gathering. Thin and cool at first, this envelope of gas gradually becomes denser, capturing more of the lightweight hydrogen and helium that drift nearby. The once naked core is now cloaked in an embryonic atmosphere, a preview of the giant it will become. By now, perhaps tens of millions of years into its formation, this protoplanet has grown to several times the mass of Earth. Its increasing gravity influences a wide region of the disk, asserting itself as a new center of attraction. Still, compared to a star, it remains a faint and cool object. No fusion burns in its core, only the slow release of gravitational energy warms it. As time passes, something remarkable occurs. When this growing planet reaches a critical mass, the balance tips suddenly. The thin shroud of gas it has been nursing for millennia begins to collapse inward faster, pulled decisively by the planet's increasing gravity. What follows is a phase of runaway growth. In a cosmic blink of an eye, perhaps only tens of thousands of years, this world swells drastically in size and mass. It's as if invisible floodgates have opened. Gas that once drifted lazily in the disk is now drawn inwards in great streams, funneling onto the young planet from all directions. From afar, one might see faint, nebulous arms of gas spiraling into a brightening point where the planet lies, like water flowing down a drain in slow motion. The planet's nascent atmosphere thickens exponentially as it greedily inhales the surrounding hydrogen and helium. Pressure and temperature in its deepening atmosphere climb, causing the infalling gas to glow faintly and the planet's silhouette to blur behind a growing halo. The rapid influx of material also causes the planet to spin faster, organizing the swirling clouds into broad bands around its equator. Within those bands, new storm systems begin to take shape, energized by the heat of accretion. What was once a modest icy core, shrouded in a whisper of gas, is transforming into a colossal sphere of cloud and storm. Deep inside, the original core is now buried under crushing layers of gas, hidden from any view. Above it, the atmosphere towers high, filled with turbulent currents. Newly formed cloud decks wrap the planet in stripes of white, yellow, and orange, and eddies of storms speckle its surface. These are the first hints of the banded appearance and mighty tempests that will one day characterize this gas giant. To a human observer, it would still seem an eternity. But compared to the eons that came before, this is an explosive growth spurt, a brief flash of metamorphosis in the planet's long life. When the frenzy ends, the newborn giant stands many times its former mass, forever changed by this quick infusion of gas. Out in the far reaches of the star's domain, our newly formed giant is not alone for long. Elsewhere in the protoplanetary disk, other massive cores follow a similar path. In one neighboring region, a second protoplanet reaches its own tipping point and begins gulping down gas, growing into a twin giant. Further out, a third large world slowly gathers itself from the cold debris. Before long, the outer solar system, once just a sparse expanse of ice, rock, and diffuse gas, boasts a family of immense new planets. These are the first of the frozen giants, forming far from the warmth of their star. Out here, the sunlight that reaches them is feeble, barely brighter than a pale twilight. Distances are so great that a newborn gas giant might take decades, or even centuries, to complete a single orbit around its sun. Seasons, if such distant worlds experience them at all, stretch on for ages. The cold is profound, with temperatures so low that even gases like methane and ammonia turn to ice. Ironically, it is this deep freeze that enabled the giants to form. The abundance of solid ices provided ample building material for their cores, and the chill helped those nascent giants hang on to the light gases that would otherwise escape. In the quiet darkness, these massive planets awaken in slow succession, each one huge and majestic in its own way. They float in their distant orbits like silent guardians of the night, cradled by the frost and the endless starry void beyond. Not every protoplanet will reach the same giant status. Some may stall in growth once the nearby gas is depleted. In our solar system, Jupiter and Saturn became massive gas giants, while the more distant Uranus and Neptune, forming later or with less to draw from, ended up smaller ice giants with proportionally more heavy elements and less hydrogen and helium. But all these worlds trace their origins to this frigid outer nursery, born in parallel from the disk's bounty. From a vantage point within this still-forming planetary system, one could witness a scene both serene and monumental. Giant planets, newborn and still gathering mass, loom as ghostly silhouettes against a backdrop of millions of stars. They bask in the faint glow of their young sun, each one tinted a different hue by the gases that compose it. One may gleam with a pale golden-white atmosphere laced with ammonia clouds. Another might have a soft blue complexion due to methane haze high in its skies. These infant giants have no solid ground to stand on. Beneath their upper clouds lies only deeper and denser layers of gas, descending ultimately to a hidden core. At this early stage, their atmospheres are warm from the energy of contraction and formation, so each giant emits a gentle thermal glow of its own. To human eyes, they would appear as immense spheres of coloured cloud, but to an infrared gaze they would shine softly, like embers left from a creation fire. Each giant is enveloped in a swirling entourage of its own, a circumplanetary disk of gas and dust orbiting the planet like a miniature version of the protoplanetary disk. Within those subdisks, smaller clumps of matter are gathering. These will become the giant planet's moons. Already, some moonlets are accreting, and faint rings of dust trace circles around their parent planets. In time, those rings may coalesce into moon systems, giving each giant a family of worlds all its own. In the end, each giant may acquire dozens of moons of all sizes, from tiny captured asteroids to huge moons with complex geology. These secondary worlds will remain bound in loyal attendance for billions of years, circling their giant planet as it circles the star. For now, though, It is the giants themselves that dominate the view, carrying a quiet warmth within them, memories of their rapid birth. They drift through the outer dark like solitary gods of the night, presiding in silence and solitude, each with a retinue of future moons, and each in a slow, stately orbit around the infant sun. In time, the chaos of creation in the disk begins to settle into order. The once thick fog of gas and dust has thinned dramatically. The young star, which was highly active in its infancy, has now blown away much of the remaining nebula gas with its intense starlight and stellar winds. What remains are the newly formed planets themselves and countless smaller remnants strewn about. Asteroids, comets, and grains of dust left like debris on a workshop floor. The inner region of the system clears out, revealing the rocky worlds that have taken shape close to the sun. Farther out, beyond a now mostly empty gap, the gas giants preside in their orbits. Between the inner planets and the realm of the giants lies a broad belt of rocky fragments that never managed to form a planet at all. Perhaps the gravitational influence of the giants kept this belt's pieces from coalescing, dooming them to remain rubble. Beyond the giants, a distant halo of icy objects, proto-comets, lingers at the fringe of the system. The star at the center has calmed from its feisty youth into a more stable brilliance. It shines steadily now, illuminating the planets that circle it. Where once there was a continuous cloud of material, now there are distinct worlds tracing clear paths around their sun. The gas giants, hulking in the outer darkness, have claimed the lion's share of the system's material. The largest of them outweighs all the inner planets combined, a testament to how much they dominated the formation process. They sit like ancient guardians at the periphery, enormous and enduring. Their gravitational influence, though unseen, quietly shepherds the structure of the entire planetary system. In the newfound calm after the frenzy of creation, a grand architecture has emerged. A bright central sun, encircled by an inner family of small rocky worlds and an outer retinue of giant planets. Roughly 100 million years may have passed since the star's ignition. Now the era of planet formation draws to a close. The major actors of this cosmic story have taken shape, and the frantic building of worlds gives way to a steadier, quieter epoch. The stage is now set with all its major actors in place, poised for the long cosmic story that will follow. Now, with the planetary system fully formed, the giant planets take on a new role as architects and enforcers of cosmic order. Their immense gravity influences the orbits of countless smaller bodies, shaping the overall structure of the system like invisible hands. Between the orbit of the outermost rocky world and the innermost giant lies a broad band of asteroids. This belt of debris is composed of rocks and fragments that never coalesced into a full-fledged planet. Jupiter, the mightiest of the giants in our solar system, can be thanked or blamed for that. Its powerful gravitational pull continually stirred up the asteroid belt during the early eons, preventing the rocky pieces there from peacefully coming together. Whenever those asteroidal fragments tried to assemble under their own gravity, Jupiter's regular tugs would disrupt the process. In a sense, Jupiter claimed that region for itself, allowing only rubble to remain. As a result, instead of another Earth-sized world between Mars and Jupiter, there is a sprawling collection of minor bodies endlessly circling the sun. Through this influence, the giant planet helped define the basic layout of the system. Smaller terrestrial planets huddle near the sun, and nothing of significant size or mass lies between those worlds and the giants. In this way, the giants acted like cosmic sculptors, carving gaps and lanes in the spread of material and ensuring each planet occupied its own distinct niche. Even Mars's modest size might be owed to Jupiter's interference. The giant likely scattered much of the material that could have otherwise merged onto the red planet, leaving Mars a comparatively small world. Thus, Jupiter and its fellow giants helped dictate not only where planets formed, but how large those planets could become. The giants can also wander from the orbits in which they were born, drifting closer to or farther from their star over long timescales. Such migrations are slow and silent in the moment, but their consequences can be dramatic for the entire system. A moving giant acts like a gravitational bulldozer, disturbing everything in its path. It can fling smaller protoplanets and asteroids aside, ejecting some from the system entirely and sending others tumbling inward. Many astronomers suspect that, long ago, the giants in our own solar system shifted positions in just such a gravitational dance. As they did, they unleashed a cascade of comets and asteroids that had been lurking in the outer regions, sending them hurtling toward the inner planets. For a period of time, the young Earth and its neighbours were subjected to an intense barrage of impacts. This hypothetical era of heavy bombardment would have reshaped the surfaces of the Moon and planets, with countless new craters. We see evidence of this ancient bombardment in the pockmarked faces of Earth's moon and the planet Mercury, their scarred highlands preserving the memory of that tumultuous time. Such a storm of incoming debris could be catastrophic. Any nascent life on Earth at the time might have been challenged by these repeated cataclysms. And yet, there may have been a silver lining. Those very impacts could have delivered water and organic molecules from the outer solar system to the inner worlds. Comets, rich in ice and carbon compounds, crashing into the early Earth, might have helped fill its oceans and seeded the ingredients for life. Without the giants stirring things up and redistributing materials, our home planet may not have received the bounty of water that makes it the blue world we know. Beyond our solar system, scientists have observed evidence of even more extreme migrations. Giant exoplanets found scorchingly close to their stars, far from where such massive planets are thought to form. These hot giants likely drifted inward over time, disrupting their systems and sweeping aside any smaller worlds in their way. In our cosmic neighborhood, we can be grateful that our giants ultimately settled into orbits that, while disruptive in the short run, allowed the inner planets to eventually enjoy long eras of stability. The Moon's heavily cratered surface still bears witness to that early raining of fire. Its silent craters are a testament to the violence the giants once unleashed before peace prevailed. Over billions of years, the presence of these massive planets continues to define the destiny of the smaller worlds around them. In the cold outer reaches, the giants reign supreme, but their influence extends far beyond their immediate orbits. Jupiter's gravity, for instance, corrals countless small bodies into its sway. It has captured swarms of asteroids that share its orbit, the so-called Trojan asteroids that travel ahead of and behind Jupiter like a cosmic entourage. Saturn, and farther out Uranus and Neptune, also subtly tug on vast populations of icy objects at the fringes of the solar system. Neptune's influence, for example, has locked some distant Kuiper Belt objects into stable resonant orbits, Pluto being a famous case, caught in a gravitational rhythm that keeps it from ever colliding with Neptune. In these ways, the giants sculpt not only the asteroid belt, but also the distant reservoirs of comets, ensuring that the debris of the solar system is distributed in belts and clouds, rather than roaming freely. The giants even communicate through their gravitational pull on the central star and on each other, creating a delicate balance that keeps the whole system in a lasting rhythm. If one could watch from afar, they would see the sun itself wobble slightly in its path, pulled by the hefty orbiting Jupiter, a subtle dance of star and planet around their common center of mass. Without the steadying influence of the giants, the inner planets might not have maintained the nearly circular, stable orbits that allow climate and conditions to remain relatively gentle over geological time. Instead, the giants serve as anchors in the cosmic choreography, their great mass helping to stabilize the gravitational ballet of all the planets. With the giants in place, the solar system achieves a long-term harmony. Each planet, large and small, tracing its path year after year, century after century after century, in a configuration that can endure for eons. Yet these giants are not benevolent guardians in every respect. At times, their gravity can be a disruptive force, nudging smaller objects onto perilous paths. Jupiter, while often shielding the inner planets by hoovering up stray comets, can also redirect trouble their way. A comet that might have harmlessly passed through the outer darkness can have its trajectory bent by Jupiter's pull, sending it swinging inward toward the Sun, and potentially on a collision course with a planet like Earth. Throughout Earth's long history, impacts from such wayward visitors have occasionally wrought immense destruction and change. One of the most famous examples is the asteroid or comet impact that occurred 66 million years ago, an event believed to have contributed to the mass extinction of the dinosaurs. It's possible that object's orbit was influenced by Jupiter or another giant, setting it on a deadly intercept with Earth. This serves as a stark reminder that Jupiter's protection is not absolute. The same gravity that can shield can also scatter hazards inward. In a sense, the giants play dual roles. On one hand, they act as cosmic vacuum cleaners, and on the other, they can be the very instigators of chaos. This paradoxical influence has deeply shaped the evolutionary history of any life that might take root on the inner planets. Periods of peaceful stability, where life can flourish and evolve, are occasionally punctuated by catastrophic impacts that reset the stage, and the giants often have a hand in both creating the peace and unleashing the storm. Astronomers have even observed Jupiter in the act of protection. In 1994, a comet fragmented and plunged into Jupiter's atmosphere, rather than continuing on toward the inner solar system. The giant planet's gravity had captured it, and Jupiter bore the brunt of the collision in a series of spectacular bursts, leaving dark scars on its cloud tops for a time. Such events show us, dramatically, how Jupiter intercepts dangers that might otherwise have menaced the inner worlds. At the same time, we know that Jupiter has also flicked many other comets sunward. Life on Earth, and on any inner planet, thus exists under the complex influence of the giants, both grateful for their guardianship and forever wary of their potential to send disaster our way. In a very real sense, life on Earth owes much to the giants' protection, even as it lives under the potential threat of their whims. Consider also that the giant planets are attended by retinues of moons, some of them as large and geologically active as planets themselves. These moons feel a constant tug-of-war between the gravity of their massive host planet and the distant pull of the Sun. Locked in intricate dances, many moons orbit in rhythmic step, resonance with one another under their planet's dominion. These gravitational interactions can stir the moon's interiors, flexing and heating them with tidal forces. On one moon, an ice-encrusted surface might hide a deep ocean kept liquid by the giant planet's incessant tugging. On another, volcanoes might erupt continuously, powered not by sunlight, but by the squeezing and kneading from its planet's gravity. In this way, giants can even nurture pockets of activity, and possibly habitability, far from the warmth of the star. It's intriguing to imagine that while the surface of a moon might lie in eternal night, beneath its ice a warm ocean could be teeming with life, all thanks to the giant planet's gravitational embrace. For example, Jupiter's innermost large moon Io is locked in an eternal tug with Europa and Ganymede, causing Io's interior to heat up and burst forth in hundreds of volcanoes, the most volcanically active body in the solar system. Around Saturn, the little moon Enceladus is similarly pulled and squeezed, so much that it sprays water geysers from a subsurface sea through cracks in its icy crust. The whole system of planets and moons is interconnected. A push or pull in one place can set off subtle echoes throughout the system. And yet, for the most part, a stable balance persists. For billions of years, the orbits of the planets and their moons continue with only gentle changes. In those eons of relative peace, life has the opportunity to begin and evolve on worlds where conditions are right, such as a small blue planet closer to the Sun. That long calm is owed in no small part to the steadying influence of the giants and their diligent clearing and guarding of the cosmic environment. They are the silent watchers at the edges of the planetary system, vast and distant, whose gravity has quietly shielded and shaped the inner sanctuaries of their system. They stand guard like ancient gods at the boundary of the solar system, immense and inscrutable. As time flows on, nothing in the cosmos remains entirely unchanged. The giant planets, though ancient and mighty, are not eternal in their present state. They have spent billions of years in quiet vigilance around their star, orbiting in the darkness and cold, largely unaltered to a casual glance. Subtle changes have been happening all along. Their internal heat has slowly diminished, their atmospheres have very gradually cooled, and perhaps some of their once turbulent weather has calmed over the eons. Deep in the heart of the system, the central star has been evolving as well. For most of its life, it has burned its fuel steadily, warming the planets with a consistent light. In its youth, it shone a bit less brightly. In middle age, it has grown slightly more luminous and stable. But even a star's supply of fuel is finite, and after a very long time, on the order of 10 billion years for a star like the Sun, that fuel nears exhaustion. When that point arrives, the star's steady glow will begin to falter and change. The gas giants, still faithfully circling in the cold and dark far away, will soon find themselves in an environment they have never experienced before. The calm equilibrium that lasted for ages is poised to end. The stage is quietly being set for a new chapter in the giant's story. A chapter of decline and transformation that follows the long era of relative calm. Eons slide by, and eventually, the once steady star at the center of this system begins to falter in its old age. Deep within the star, the simple fuel that sustained its brilliance is nearly spent. Gradually at first, then more rapidly, the star undergoes a dramatic transformation. It swells in size, bloating outward into a gigantic form. What was once a familiar yellow-white sun becomes a colossal red star. Its outer layers expand and cool, shifting the star's hue to a deep orange red, even as its overall brightness increases tremendously. From the perspective of the distant gas giants, this change is monumental. The small white disk of light that for billions of years gently illuminated their skies grows into a vast amber orb. Each day, the sun looms larger and redder until it dominates a significant portion of the sky. No longer a pinpoint of brilliance, it has become a great glowing bulge on the horizon, casting a coppery light over the cloud tops of the giants. The temperature in the outer solar system begins to climb, though even now it remains cold by human standards. Frozen moons that have spent eternity in deep freeze begin to feel the touch of warmth. On some of these moons, surface ices of nitrogen or methane start to sublimate, turning directly into gas, and a thin, temporary atmosphere hazes their horizon. Saturn's moon Titan, for instance, has been frigid for eons. Now, under the red giant's glow, its methane lakes begin to evaporate, shrouding the moon in thick golden clouds. Distant icy worlds like Pluto might awaken with a fleeting atmosphere as their surfaces thaw slightly. For the giants themselves, the infusion of warmth stirs their upper atmospheres. Jet streams shift, and clouds rearrange into new patterns. Colors deepen under the ruddy light. Hues of copper, rose, and gold bloom in the previously muted bands of Jupiter and Saturn. Storms that had long been stable may wane, or others may intensify, as the energy balance in the giant skies changes. In the deep cold that once defined the outer reaches, a strange new season has arrived. A brief, unexpected summer, granted by a sun entering its sunset years. Closer to the engorged star, profound upheavals are underway on a scale even more dramatic. The innermost planets are overwhelmed by the sun's expansion and intensified luminosity. Mercury and Venus, the planets nearest the sun, are completely engulfed by the star's bloated outer layers, vaporized without a trace. Earth, a little farther out, faces a dire fate as well. Its once blue oceans have long since boiled away into space, and its lands are scorched far beyond the point where life can survive. Indeed, as the sun's swollen photosphere reaches outward, it may consume Earth entirely, or at least strip it of all that made it Earth-like. Whether Earth is eventually swallowed whole by the advancing wall of stellar fire, or left as a charred, lifeless cinder circling a dying sun, in either case, it is utterly unrecognizable. Mars, which sits just beyond Earth, might barely escape being devoured, but it does not escape ruin. Any lingering water ice or atmosphere on the red planet is stripped and baked off, leaving a barren, baked desert even more desolate than before. From the distant vantage of Jupiter or Saturn, the inner regions of the solar system are now aglow with a diffuse light. What was once the realm of bright, solid planets is replaced by the nebulous, burning envelope of the star itself. The view inward is obscured by a brilliant, hazy radiance, the sun's swollen atmosphere extending outwards and drowning everything it touches. It is a silent cataclysm unfolding in slow motion. No sound can carry across the vacuum of space, but the sight is one of slow, inexorable destruction. The giants, however, remain at a safer remove. They watch the demise of their smaller siblings from afar, illuminated by a sky now filled with the murky, reddish glow of a dying sun. This transformation occurs over a relatively short time in cosmic terms, some tens of millions of years to expand, and the red giant stage itself lasts only a few million more. As the red giant sun reaches its bloated zenith, it also begins to shed its own substance in earnest. The outer layers of the star are not gravitationally bound as tightly as before, and they start to flow outward in a massive stellar wind. This is no gentle breeze, but a relentless outpouring of solar matter, particles and gas streaming away into space. The entire solar system is gradually enveloped in a diffuse, glowing nebula of the star's cast-off material. From the perspective of the surviving planets, it is as if the vacuum of space has become filled with a thin fog of luminous gas. The gas giants find themselves awash in this expanding envelope. Wave after wave of hydrogen, helium, and traces of heavier elements blown off the sun wash over them. The effect on the giants is significant, but not catastrophic. The fierce stellar gale strips away the outermost wisps of their atmospheres and heats the layers above their clouds. Each of the gas giants may even grow a tenuous tail of evaporated gas, streaming behind it like a faint comet as it plows through the red giant's outflow. Still, these planets are colossal and held together by their own strong gravity. The star's shedding, though intense, can carry away only a small fraction of their mass. Instead of destroying them, the main impact of the stellar wind is to push on the giants and alter their orbits. As the dying star loses mass, its grip on the planets weakens. Freed from some of the sun's pull, the gas giants drift gently farther from the sun, their orbital paths expanding outward. It is as if they are giving the dying star a wide berth, respectfully backing away as it undergoes its convulsive transformation. By the end of this convulsive shedding, the sun may have lost a substantial fraction of its mass, nearly half, to space. Through it all, the giants ride out this storm of stardust and plasma, battered but intact, awaiting the next stage in the drama of their star's death. Eventually, the red giant's expansive phase reaches its climax. Having cast off a significant portion of its mass, the star can no longer hold on to its expanded form. Its outer layers push farther and farther into space until, at last, they detach completely, drifting outward as a magnificent, luminous cloud. For a brief, wondrous time, the system is graced by a phenomenon known as a planetary nebula, a glowing shell of gas expanding into the void, illuminated by the hot remnant of the star at its center. This nebula shines in soft hues of pink and green, with filaments of red and blue, as the heated gas fluoresces under the energetic light of the exposed stellar core. To the giants, this nebula might appear as a ghostly veil cloaking the inner regions, a final ethereal monument to their sun's former glory. Within that nebula lies the star's last gift to the universe, the elements it forged in its lifetime, carbon from its depths, along with oxygen, nitrogen, and more, now flung into space to enrich the cosmic clouds. Ultimately, this material will drift into the galaxy and mix with other interstellar gas, seeding the formation of new stars and new planets in a cosmic cycle of rebirth. But in the here and now, the nebula gradually expands and thins, becoming less bright as its gases spread out. A few tens of thousands of years pass, a mere heartbeat on galactic timescales, and the once majestic nebula fades from view, its content dispersed into the surrounding darkness of space. At the center of where it all began, only the core of the star remains. What was once a bloated red giant has collapsed into a white dwarf, a small, dazzling point of light, no larger than Earth, but incredibly dense and hot. This stellar ember is the shrunken heart of the sun, now laid bare. It shines a brilliant white blue with intense heat, though its light is but a fraction of the sun's former glory. With the emergence of the white dwarf, true night falls over the remaining planets. The sun has shrunk from a bloated giant to a tiny, brilliant spark at the center of the system. From Jupiter's vantage, the sun is now a point of searing light, perhaps as bright as Venus once was in Earth's sky, but no longer a sun-like disk. Daytime on the gas giants has become a perpetual twilight. On the side of each planet, facing the white dwarf, a weak silver glow prevails, enough to cast faint shadows, but far dimmer than the golden daylight they knew for ages. The other side of each planet is engulfed in darkness as deep as interstellar space, with only the distant stars to provide pinpricks of light. The temperature in the outer solar system plummets swiftly. The brief warmth the giants enjoyed during the red giant phase dissipates into space, leaving them colder than ever. Their own internal heat, too, has largely leaked away over the billions of years of their existence. And now, with negligible sunlight to stir their cloud tops, the planets descend into an unprecedented chill. Jupiter's multicolored cloud bands, once vibrant with belts of orange, white, and red, grow muted and dim under the feeble illumination. Any great storms still persisting, like Jupiter's centuries-old Great Red Spot, finally lose their vigor and shrink, the energy needed to sustain them no longer available. Saturn's iconic rings, now lit only weakly, fade to near invisibility against the black sky. The perpetual electrical storms that once flickered in the giant's deep atmospheres become increasingly rare until they cease altogether. Yet, even in this extreme darkness, not all warmth vanishes. Deep within certain moons of these giants, tidal forces continue to generate heat. One can imagine that beneath the miles-thick ice crust of a moon like Europa, a hidden ocean might still persist, kept liquid by the gentle kneading of gravity. If any simple life had ever thrived in Europa's dark seas, it could continue its quiet existence for a time, oblivious to the loss of the sun in the sky above. In the dim aftermath of the star's collapse, the gas giants stand truly as frozen giants. Immense spheres of cold, inert gas resting under the faint glow of a dying star. Even farther from the now diminished sun, the outermost giant worlds, Uranus and Neptune, fall into an even deeper quiet. These distant ice giants, once whipped by supersonic winds and adorned in vivid turquoise and cobalt hues, are now almost completely dark and still. Their blue-green colours, a result of methane in their atmospheres reflecting sunlight, fade into near blackness under the paltry illumination of the white dwarf. The methane that once gave Neptune its rich blue tint begins to condense and freeze out of the atmosphere. High in what remains of their cold skies, thin clouds of exotic ices form and then drift downward, disappearing into the haze. Without sunlight to drive weather, Uranus and Neptune's atmospheres stratify into motionless layers. The fierce winds that once circled Neptune, the fastest in the solar system, slow to a stop. One by one, the moons of these giants are plunged into almost total darkness as well. A world like Titan, which for a short time emerged from cold obscurity during the red giant days, now sees its temporary summer collapse into a winter colder than any before. Titan's thick haze freezes and falls back to the surface. Methane rains that once fell now lie trapped as ice in lake beds that will never thaw again. If an observer could somehow stand on one of those outer moons now, they would see their giant planet looming as a vast, dark shape against a starfield, illuminated only by a pinpoint where their sun used to be. The temperature on these worlds approaches the ultimate cold of space. In the shadows, parts of their atmospheres are only a few degrees above absolute zero. It is as cold now as the wider universe itself, only a few degrees above the cosmic background temperature that permeates space. Gases that never could have frozen before, like residual hydrogen or neon, may now precipitate out as rare ices, coating portions of the upper atmosphere like frost. It is an almost inconceivable cold, an endless cosmic winter that has settled over the outer solar system, still and silent. What becomes of the giants in the eons that follow the death of their sun? They continue to orbit the faint stellar ember at the centre, faithfully circling in the dark. Having moved farther out due to the sun's reduced mass, they now trace larger, slower paths around the white dwarf, like distant sentinels. With each passing billion-year interval, the white dwarf itself cools and dims a little more, slipping gradually from white-hot to yellow, then red, and eventually into the infrared and darkness. As the star fades, the gas giants continue to cool in tandem. Deep inside each planet, the last remnants of heat from formation and long-ago contraction seep away. Jupiter, Saturn, Uranus, and Neptune slowly transform in composition and appearance as the temperature drops. Hydrogen, which has always made up the bulk of their atmospheres, may start to behave less like a gas and more like a supercold liquid. In the upper layers of these giants, the distinction between gas and liquid blurs as the cold and pressure cause a continuum, Perhaps vast oceans of fluid hydrogen form, floating atop deeper mantles of metallic hydrogen. Helium and other gases that once swirled freely might begin to settle or even rain down towards the planet's centers in slow drizzles. Any water deep in their atmospheres has long ago frozen out or been locked into icy compounds. Their central cores of rock and ice, once searing hot during formation, are now frigid and solid. In essence, these planets have become enormous frozen droplets, cosmic snowballs composed not of water ice, but of hydrogen, helium, and other gases turned solid or liquid under crushing pressure and extreme cold. They remain intact and quietly floating, gradually grinding toward a final equilibrium temperature that is only a hair above the ambient temperature of space. Trillions of years in the future, that white dwarf will itself cool to a black dwarf, a cold, dark sphere of ash, leaving the planets with no star at all. It is a peaceful, if desolate state, after the tumultuous winds and storms of their youth and the long vigil through their star's life. The giants have entered a phase of almost perfect stillness. They simply exist now, vast and silent, in an endless night, their evolution essentially complete. Drifting through this eternal night, the gas giants have become almost perfectly silent sentinels. If one could descend into what remains of Jupiter's atmosphere now, they would find an uncanny stillness, perhaps only a faint whisper of wind, or nothing at all. The once dramatic interplay of clouds, storms, and sunlight has ceased. Those thick bands of clouds that long ago flashed with lightning and swirled with tempests now lie as stagnant layers of mist, lit only faintly by the far-off stars and the occasional spark of a cosmic ray. Time itself seems to lose meaning in this quiet. 1,000,000 years might pass, like a gentle night, unmarked by any change on a world where even a breeze has become a rarity. The giants have entered a deep cosmic slumber, a state of profound quiescence that could last essentially indefinitely. Yet, the story of these frozen worlds might not be completely over. In a universe that may continue for trillions of years, even worlds seemingly locked in unchanging stillness can eventually encounter something new. The gravity of a passing star could, by chance, intrude upon the solitude of the giants. If a rogue star or a nearby stellar neighbor drifts too close, its gravitational pull might tug one of the gas giants away from its ancient orbit, perhaps even stealing it to become part of a new solar system, or flinging it into interstellar space. On an even grander scale, galaxies themselves will collide and merge in the far future. In several billion years, the Milky Way will merge with its neighbor galaxy, and such cosmic upheaval could scramble the arrangements of stars and planets. During that event, or others like it, some of these ancient worlds might be cast adrift, turned into rogue planets wandering the galaxy alone. A gas giant that spent its life bathed in sunlight could find itself ejected, voyaging through the interstellar abyss with no sun at all, carrying only the memory of a star long gone. Even in that cold exile, it would remain a colossal globe of gas, now truly in perpetual night, virtually undetectable except to the keenest observers. Silently, it would traverse the galaxy, a wanderer born from one sun and now untethered under the light of myriad others. Across the cosmos, there are likely many such frozen giants, wandering or keeping vigil around stellar remnants. Our own gas giants may one day be counted among them, but they are certainly not alone. Astronomers have found hints of planets that drift through space without a sun, rogue worlds untethered and starless, detectable only through the slightest gravitational tug they exert on starlight as they pass by. Others have been discovered still orbiting the tiny embers of stars long gone. In fact, one Jupiter-sized planet was recently observed circling a white dwarf, offering a glimpse of what our solar system's far future could look like. Each of these planets has its own tale. Perhaps it was once a vibrant, banded giant basking in the light of a youthful star, now left as a dark, frozen relic after that star's demise. Another might have been thrown free of its home system by gravitational turmoil, doomed to roam the galaxy forever. It's estimated that billions of such orphaned planets wander the Milky Way, outnumbering the stars themselves. And while our solar system's giants ended up in cold exile, some giant planets in other systems will meet even more violent ends. Those that orbit too close to their suns may be completely obliterated or consumed when their stars swell and die. There is a profound, somber beauty in the final transformation of these worlds. In their silence and stillness, they hold the history of their long-lost solar systems within them. Layer upon layer of their atmospheres contains the record of billions of years of cosmic change, chemical traces of the bright days when their star shone, the turbulent epoch of their star's death, and the gradual cooling that followed. Their continued existence is a testament to the longevity and resilience of planets. Long after their stars have died, the giants persist, stoic, unyielding, and patient against the backdrop of the universe. They drift through the galactic night with an almost eternal patience, monuments to the worlds that once were. Picture, if you will, some far future travelers venturing into this quiet remnant of a solar system. Approaching the center, they would find a pale, small star where a vibrant sun once blazed. At first, they might not even notice the planets, for those great worlds no longer reflect much light. But with patient observation, the travelers would detect them, enormous, darkened spheres still circling at great distances. They would steer their ship toward the faint beacon of the white dwarf and pass by what remains of the planets. Perhaps they would glimpse Jupiter's hulking form only by starlight glinting off its cloud tops, or see the silhouette of Saturn's rings as a thin line against the starry background. They would find the once blue Neptune now, a ghostly grey ball with no hint of its former colour. If those travellers dipped into a giant planet's atmosphere, they would encounter almost no weather, just calm, frigid haze stretching as far as the eye could see. In the immense silence, they might reflect on the fact that these ancient worlds had outlived their sun. They circle on, lightless beacons of a story long since played out. To the travellers, it would feel like wandering through a cosmic ruin, the grand temples of a solar system still standing, but emptied of the fiery spirit that once illuminated them. And so, in the quiet after the star's life has ebbed away, we leave the gas giants in their ancient repose. From swirling cradles of dust and gas they were born, and under the gentle care of their sun, they grew into mighty guardians. They danced through the cosmic ages, shaping the destinies of the worlds around them. In time, they bore witness to their star's fiery last act, and survived to see the tiny ember that remained. Now they drift in an endless twilight, frozen giants carrying within them the echoes of creation. Their fate, though seemingly a cold and lonely one, is also a peaceful rest at the end of a very long journey. On the grand timeline of the universe, even this quiet epoch is but a chapter. Someday, perhaps in trillions of years, The materials that compose these giants will be stirred up and scattered, maybe by a chance collision or the tides of the galaxy, eventually to mix into new nebulae. In that way, parts of these giants could become the seeds for new stars or planets, and the cycle of cosmic birth and death would continue. But for now, they simply remain vast, silent, and serene. In the darkness that follows the final sunset of their star, these dying gas planets keep their silent watch, enduring as some of the oldest storytellers in the universe, each one a monument to the saga of a solar system that once was. There is a sense of reverence in this final scene, a hush that falls after the long story, filled with the understanding that even in cosmic endings, there is a kind of peace. As long as matter endures, they will quietly bear witness to all that came before. Our journey into the giants continues, plunging into the endless sky of swirling gas. We glide down through layer after layer of clouds, the gentle hum of turbulent winds our lullaby. In Jupiter's atmosphere, vast bands of gas stretch across the sky. Dark brown belts and pale cream-coloured zones flowing in opposite directions around the planet. Each stripe of cloud moves with a mind of its own, pushed by jet streams and fed by deep convection. Above all, drifts the Great Red Spot, a colossal cyclone larger than Earth itself, brooding in the clouds for centuries. Its colour and longevity remain mysteries, sometimes deep crimson, sometimes a washed-out salmon, as if the spot is slowly evolving. Long ago it was easily twice as wide as Earth. Now it has shrunk to just larger than our world. Yet this storm still rages, a living emblem of Jupiter's restless weather. Saturn's sky is gentler in colour, but no less alive. Its atmosphere drapes the planet in soft shades of gold and tan. Faint stripes and belts run around the globe, whispering of winds and storms beneath. Each pole hosts its own marvel. At the north, the famous six-sided jet stream known as the hexagon, a geometric storm hundreds of kilometres across, spinning in eerie perfection. At the South Pole resides an unending hurricane with a clearly defined eye, thousands of kilometres wide, glowing in the dim, shadowed light. Invisible currents race across the vast planet, winds reaching hundreds of metres per second, 3 times faster than Earth's fiercest hurricanes, carrying clouds in epic sweeps. And roughly every few decades, Saturn unleashes a great white spot, a storm so massive it encircles the entire planet. The last such outburst in 2010 to 2011 piled clouds kilometres high, briefly painting a brilliant white belt around Saturn before gradually fading over years. These periodic tempests remind us that even the gentler ringed world can unleash huge energy from within. Amid these swirling skies, violent storms occasionally break through the clouds. Lightning flashes in Jupiter's dark bands, bolts far more powerful than any on Earth, illuminating the rolling cloud layers with brief, silent fire. Saturn, too, roars with furious storms, hidden beneath its haze. Cassini detected a colossal 2011 thunderstorm on Saturn's night side, so bright it lit up the entire globe. Even in the quieter zones, Jupiter hides surprises. Infrared hotspots occasionally puncture its cloud tops, clear holes where heat leaks from deep down. NASA's Galileo probe plunged into one such hotspot and found much higher temperature and deeper sunshine, evidence of descending air and open skies. These features show that even where no storm is visible, the atmosphere is far from uniform. It is alive with hidden weather. The lightning on these giants dwarfs our own. One flash on Jupiter can light a region thousands of kilometers wide. Scientists have recorded thunder so enormous that it can be seen by amateur observers on Earth. Each lightning discharge injects energy into the sky, fueling chemistry and even audible crackles in space. High above the clouds, the sky is a kaleidoscope of layers. The clouds themselves form a layered wonderland. High in the atmosphere lie clouds of ammonia ice, frosty and white. Below them, at greater pressure, other substances condense. On Jupiter, ammonium hydrosulfide forms hazy brown bands between the white clouds. Deeper still, at immense pressure, water clouds exist, akin to Earth's rain clouds, but buried far below. When we gaze at these planets, we see only the topmost veils, the brilliant white of ammonia crystals and the darker belts beneath. These layers paint the palette. Saturn's golden and tan hues arise from tinted ammonia clouds laced with other ices. The great red spot may owe its ruddy colour to chemicals dredged up from deep layers or altered by sunlight. Rising plumes of gas can cross these boundaries, bringing up fresh ice that brightens a belt or feeding a storm from below. None of these giants has a solid surface for an observer to stand on. The deeper we descend, the denser the gas becomes, smoothly transitioning to a liquid-like state. There is no ground beneath the clouds. Instead, the pressure grows until the hydrogen behaves like a fluid ocean. Under this weight, even helium and hydrogen, normally light and transparent, take on exotic forms. Hydrogen becomes a metallic fluid that conducts electricity like a metal. In these depths, familiar materials become alien. At Jupiter's core, pressures reach tens of millions of times Earth's atmospheric pressure, and temperatures exceed those on the Sun's surface. We imagine the center to be a glowing inferno, a sea of metallic hydrogen caressed by intense heat. Models suggest a core of heavier elements, rock and ices maybe 10 times Earth's mass, lurks at the heart, but it might be diffuse. NASA's Juno probe has found evidence that Jupiter's core could be blended into the deep envelope, not a neat solid ball. In any event, gravity has squeezed the very atoms of hydrogen so tightly that they share electrons, forming a giant dynamo. Electrons flow like water in that metallic interior, generating the planet's powerful magnetic field. If we listened carefully, we might hear the faint hum of this hidden dynamo, the internal heart that powers the planet's magnetism. Jupiter's field is the strongest in the solar system, a vast bubble swallowing even Saturn's orbit. Flying through it would feel like being caught in invisible currents, charged particles spiraling along magnetic lines and igniting auroras brighter than Earth's. Saturn's interior works similarly, though its magnetic field is weaker. We've seen the evidence, glowing ovals of light hovering over their poles, where charged particles rain down and the sky itself glitters in green and pink flames. Not all giants are alike. Uranus and Neptune, the ice giants, wear coats of blue-green. In the dim light, far from the sun, these colours are surreal. On Uranus, the tint is pale cyan. On Neptune, a vivid sapphire. Unlike Jupiter and Saturn, they are rich in heavier ices of water, ammonia, and methane. The methane gas absorbs red light and scatters blue, painting their skies in these hues. Under those hazy clouds lies a different structure, a deep mantle of slush, water, ammonia, and methane ices under pressure, above a rocky core of a few Earth masses. Hydrogen and helium form only a thin outer layer. This makes them denser than the gas giants. Neptune, at 17 times Earth's mass, is still massive, but small compared to Jupiter's 318. Their climates are fierce in their own way. Voyager 2 revealed Neptune to be a stormy world, a great dark spot, an anticyclone as large as Earth, roared in its atmosphere with winds over 2,000 kilometers per hour, the fastest in the solar system. Voyager saw it disappear by the late 1990s, replaced by new storms, showing how Neptune's weather constantly changes. Thousands of kilometers across, these vortices are like holes in the methane clouds, with bright, white companions on their edges. In 1994, Hubble witnessed a second giant storm where Voyager had left off. These are not subtler versions of Jupiter's red spot, but powerful, dynamic tempests driven by Neptune's internal heat. Uranus, by contrast, appears eerily calm. Its smooth, pale disk showed almost no features when Voyager flew by. Uranus's secret lies in its tilt. Tipped 98 degrees on its side, one pole faces the sun for decades, while the other hibernates in darkness. When its seasons flip, faint storms briefly awaken. In 2007 to 2008, around equinox, bright methane clouds erupted on Uranus, surprising us with sudden activity. Modern telescopes even detect radio bursts from Uranus's aurorae, a hint of unseen churning. One wonders, did the titanic impact that tipped Uranus somehow lock away its heat? Neptune does not share this fate, and indeed Neptune emits more internal heat, which may explain its perpetual storminess. In any case, even these quiet giants can hide fury under their blue veils. Both Uranus and Neptune have moons and rings, though far more subdued than Jupiter and Saturn. Uranus has 27 known satellites, mostly small, icy worlds, and a set of 13 thin, dark rings discovered in 1977. Neptune has 14 moons and several faint rings with bright arc segments. These rings are made of dark ice and rock, barely visible. They serve as a reminder that ring systems are not unique to the brilliant worlds nearby. Even in the dim outer reaches, debris can coalesce into rings. Each moon orbits steadily in the planet's gravity, an ecosystem of its own. Uranus's moons, Titania, Oberon, and the rest, are frozen chunks of ice and rock with heavily cratered surfaces. Neptune's largest moon, Triton, captured into a retrograde orbit, has active geysers, showing these systems can be lively too. Like all their brethren, the ice giants shepherd these satellites with the same balance of gravity and pressure that holds the planet itself together. Our four giant planets, Jupiter, Saturn, Uranus, Neptune, share a family resemblance. All are swirling, massive worlds compared to the tiny rocky worlds inside. Yet when we step back and look at them together, their differences stand out. Jupiter and Saturn are gas giants of hydrogen and helium, dressed in bands of colour, glowing faintly from internal heat. Uranus and Neptune are smaller, colder, and rich in ices, painted in blues by methane. But whether near or far, these cousins are held by the same forces. And even beyond Neptune's orbit lie cousins around other stars. Indeed, the galaxy is full of gas giants beyond our solar system. Thousands of exoplanets have been found, and many are giant worlds. Some orbit their stars at gentle distances, others cling so close that they are scorchingly hot. These alien giants come in all sizes. Some are larger than Jupiter, puffed up by heat, while others are smaller, closer to Saturn's mass. In one class, the hot Jupiters, a planet orbits so near its star that it circles in days or even hours. On one such world, 51 Pegasi b, a year lasts only 4 Earth days. The day side is a furnace of 2000 Kelvin or more. Clouds would vaporize and iron gas would form. Winds likely race at tens of kilometers per second, a storm connecting perpetual day and night. We've even measured water vapor and exotic clouds on some of these worlds. One, KELT 9b, is so blisteringly hot, over 4000 Kelvin, that metals evaporate and its atmosphere glows in visible light. Others, like WASP 12b, are being torn apart by their stars, trailing ghostly streams of gas. At the other extreme are the cold wanderers. Some gas giants orbit far from their stars, receiving almost no starlight. In the deep freeze, they cool and shrink. Some may even break free entirely, drifting through interstellar space alone. Rogue planets, lost to any star. We detect hints of these by gravitational microlensing and infrared surveys. In darkness, they glow only from residual heat. If you were near one, you would see a black, frozen world, only barely warmer than the cosmic background. These dark giants may be numerous, silent sentinels in the dark galaxy. Between these extremes lies a rich tapestry of varieties. Some exoplanets have wildly eccentric orbits. One known as HD 80606b swings out far from its star, then swoops in close. In just hours, its temperature rockets from near freezing to over 1200 Kelvin and then plunges again each year. Others orbit two suns together in a cosmic dance. We have found planets around pulsars, dead stars, and even around dim white dwarfs. And some so-called super Jupiters blur the line with brown dwarfs. They may be so massive that brief deuterium fusion flares can occur, almost like a star briefly flickering. Everywhere we look, nature's imagination is boundless. We have glimpsed gas giants with unusual compounds in their skies, from metal clouds on hot worlds to colourful hazes on cooler ones. One planet, HD 189733b, appears a deep cobalt blue. Another, TRES 2b, is blacker than coal, reflecting almost no light. Clouds of silicon, titanium, sulfur, and exotic chemicals form in these atmospheres. We've even measured helium streaming off an exoplanet, like a giant balloon slowly deflating under stellar winds. Statistical studies are revealing how common these giants are. Surveys show that a significant fraction of Sun-like stars host giant planets. Hot Jupiters are relatively rare, a few % of stars, but cooler Jupiters at Earth-like distances may be far more common. Early data suggest about 1 star in 5 has a Jupiter-mass planet. As detection methods improve, we're finding analogues of our own Jupiter on long orbits. And telescopes of the future, like the James Webb Space Telescope and huge ground-based observatories, will let us directly image more of these worlds and dissect their atmospheres, learning wind patterns, cloud compositions, and even day-night temperature maps. Each new discovery broadens the definition of what a gas giant can be. In all this variety, a common thread remains. Each giant planet, near or far, is held together by the delicate balance of forces. Gravity pulls each layer inward, while pressure, from heat or motion, pushes outward. Deep inside, heat from their formation and slow contraction inflates the gas, exactly countering gravity. During formation, as these planets accreted gas, the infalling material released energy and became hot, which in turn provided pressure to halt collapse. Over time, they settled into hydrostatic equilibrium, literally a standing water balance, where every drop of gas is in pressure balance. In the case of Jupiter and Saturn, convection and internal heat maintain an outward push. In the ice giants, A slushy fluid mantle provides stiffness. The rapid spin of each planet contributes, flattening the shape so slightly at the equator, but by and large, each layer finds its resting place. Today, these giants slowly radiate away their heat. Jupiter still emits about 1.6 times the power it receives from the Sun. Saturn shines even more brightly in infrared due to extra heat from processes like helium rain inside. Neptune, too, beams out more warmth than sunlight feeds it. Only Uranus seems unusually bland, putting out nearly just what it gets in. Over billions of years, their heat leaks away, and they contract slightly. Models suggest Jupiter was about 20% larger when young, now very slightly smaller as it cools. Each decade, they lose just a tiny fraction of their power. On human timescales, they seem eternal. A decade only saps a tiny spark of their inner furnace. Even so, this balance is not unbreakable. We have already seen it nudged. For hot giants close to their star, intense radiation can blow off atmosphere like a wind. Astronomers have observed exoplanets losing hydrogen in great tails, a process that over eons could strip a gas giant down to a rocky core. In the far future, even without a fiery star close by, subtle changes will come. Our sun will one day swell into a red giant, losing mass and altering the orbital dance. The orbits of Jupiter and Saturn will shift slightly outward. A close stellar encounter in the distant future could jolt a planet out of its path, and gravitational tides could eventually draw Saturn closer, or send the ice giants adrift. In essence, no planet's state is eternally fixed. The gas giants have lasted through the age of dinosaurs, but they too will ultimately fade. Billions of years from now, their internal fires will be nearly spent, their storms quieted, leaving behind cold, dark worlds. But for now, they stand as majestic titans, enormous, graceful, and exquisitely balanced. Each day that balance holds is a testament to the equilibrium of forces within and around them. The question remains, as we shift our gaze beyond the clouds, will that balance always hold, or will time eventually tip the scales? The answer to that question lies ahead, in the final chapter of their story, a story still in the making, among the stars. In the silent reaches of space, a star burns steadily, its life slowly waning. For trillions of years, it has been a constant furnace, fusing hydrogen into helium and bathing its planets in light. But even stars have lifetimes, and eventually the fuel at their cores begins to dwindle. As the hydrogen is consumed, the star's core shrinks and its outer layers swell. The once gentle, yellowish-white sun will transform into a red giant, massive, luminous, and fiercely hot at its surface. This grand metamorphosis marks the beginning of the end for the star's planets. Deep within its heart, the star's nuclear furnace transitions to a new fuel. Hydrogen fusion peters out as helium accumulates in the core. A sudden flash of helium fusion then ignites, causing the star to brighten dramatically for a time. From the surface of any orbiting planet, the sun's glow would intensify, warming worlds that have long been cold. For gas giants far from the star, this means a new torrent of radiation. Even these distant behemoths feel the change, their upper atmospheres briefly heating and glowing from the star's wrath. This is a final banquet of light, as if the star throws off its former identity in a blaze of glory. But the star's swan song is ultimately brief. Its atmosphere swells outward, and luminosity climbs even higher. The great planets that once orbited peacefully must now face a scorching onslaught. Mercury and Venus are doomed, engulfed first in the star's fiery expansion. Even Earth could be consumed or scorched beyond recognition. The habitable zone marches outward. Some worlds may momentarily flourish in warmth. Jupiter and Saturn, the giants of our system, bask in unprecedented light, though it's a fierce light, not a gentle sun. Gradually, what were once cold orbits grow dangerous as the star's surface nears. As the star expands into a giant, it sheds mass by casting off colossal shells of gas. The loss of stellar mass weakens its gravity, so the surviving planets drift onto wider orbits. Each planet's year lengthens, and the entire system grows more diffuse. Mercury and Venus are no more, and Earth's orbit may carry it far from the dying sun or pull it in. Far beyond, the great gas giants begin to move outward slowly. Imagine Jupiter, once at 5 astronomical units from the Sun. It might slide to 10 or more. Neptune, in turn, could double its distance, pushing the Kuiper belt along with it. Even the orbits themselves are rearranging. As gravity weakens, one planet's path can cross another's without causing a collision. Subtle new resonances form as the giants shift, with their orbits gently altering each other's motion. Trojan asteroids and the rings of planets feel the change too. New configurations emerge. The vast asteroid belt, shaped by Jupiter's pull for eons, changes its character. Comets from the distant Oort cloud may even wander closer as the sun's reach diminishes. In this widening spiral, the system dances to a slower tune, each world finding a new rhythm in the cold depths. Even the interplay between worlds grows stranger. What was once a stable dance becomes a gentle sway. If two giants wander closer, their mutual gravity might nudge each other in surprising ways. A moon caught at the edge of a giant's pull could be stolen by another. Yet these interactions are slow and ponderous, like dancers learning a new, quiet choreography. Planetary motions evolve, but seldom violently, more like planets shifting seats at a long cosmic table. The old order is dissolving, and a new, more relaxed order is forming in the wake of the star's decline. As the red giant stage approaches its peak, the star can grow violent. It may pulse in brightness or shed layers in brief outbursts, each one a small death throe of its fading glow. Eventually, the swollen star will throw off its outer veil into space, forming a colourful nebula of gas around the remaining core. All that remains is the hot, dense core, a white dwarf, glowing with a faint but steady light. The surviving planets, now on wider orbits thanks to earlier shifts, circle this cooling ember. The bright sun they once knew has become a dim, cooling cinder. Even this faint light will dwindle, leaving the planets in growing darkness over the eons. Across the galaxy, stars of all kinds meet similar ends. Some massive stars explode in brilliant supernovae, shredding anything too close. Our star, by contrast, will quietly swell into a red giant and then fade into a white dwarf. Smaller stars will age even more gently, but none escape this cycle of change. For any planet, the sun it knew will be gone. Gas giants face the same fate, whether engulfed by expansion, blasted by radiation, or simply left orbiting a faint ember. Their days in the light are numbered. Whatever happens, the end result is a dark and cold fate. Each giant planet becomes a wanderer in a dimmed system, under the rule of a fading star. A star's life can be likened to a slow, grand sunset. For eons, it burns with steady light. But eventually, this brilliant orb begins to dim and redden. Planets that once lay under its warm, bright noonday shine will one day see their sun's face turn the colour of fire and then fade. It would be a transformation of sublime beauty to a distant witness, but for the worlds below, it heralds the end of an era. As the star's glow softens to a deep red, and then to the faint light of dying embers. The familiar sky will remain unchanged, while the meaning of each night shifts. The constellations do not move, but the light that defines day and night grows ever weaker. Soon, what was day may feel like twilight, and night like an endless dusk, as the star quietly slips away into memory. Meanwhile, around each gas giant orbits a family of moons, worlds held fast by the planet's gravity. These moons are companions that have circled together for eons. But as the giant's own strength wanes, the bonds that keep them together loosen. The fate of these moons becomes intertwined with the fate of their parent. Some may find themselves gently slipping away, freed from their old orbits. For a while, they may remain together, but eventually, each moon must find its own destiny. Freed from the giant's grip, a moon might settle into a new orbit around the star, becoming a tiny planet in its own right. Others might drift far enough to wander alone in space, orphaned travelers cast adrift by cosmic change. Those drifting moons undergo their own quiet transformations. Freed from the giant's warming embrace, they slowly cool and darken. Their surfaces freeze, and any atmosphere they held begins to thin or vanish. A moon like Io, once volcanically active under its giant's influence, may see those fires finally sputter out as internal heat fades. Titan, heavy with orange haze and swirling methane, could lose its shrouding fog and lakes, freezing into a cold, silent plain. Even watery moons like Europa may see their hidden seas slowly solidify beneath an ever-thickening ice crust. In the end, each moon becomes a silent shadow of its former self, a quiet echo of the vibrant world it once orbited. Even the invisible defenses of a giant planet can fade. The largest gas giants generate powerful magnetic fields that shield their moons from cosmic radiation and charged particles. But as the planet cools and its deep churning slows, this dynamo weakens. A shrinking field means less protection. A moon like Titan or Ganymede may find its atmosphere sputtering away under relentless cosmic bombardment. Without this magnetic shield, each moon becomes a lonely outpost in deep space. Any atmosphere and surface features would slowly erode under the invisible winds of the cosmos. In the end, what remains is a barren shell, a silent witness to its world's ancient history. Without the heat from their giant parent, moons lose their inner vitality as well. Tidal forces that once flexed these moons now barely whisper. Their lava lakes and cryovolcanoes sputter and die. The fiery eruptions of Io would fade, leaving only solidified lava plains behind. Enceladus, which once spouted geysers of water, would fall silent as its subsurface ocean freezes beneath the ice. Even Earth-like worlds lose their core heat over time. Without tidal stirring, their molten hearts cool. Each moon reverts to a quiet, lifeless land, the memory of its internal fires locked in stone. Even a planet's rings will not remain the same. Saturn's glittering rings, born of countless icy fragments, rely on a delicate balance of gravity and cold. With the planet's environment changing, the rings too will evolve. Warmer temperatures from the expanded star can cause the icy particles to gradually vaporize or clump together. At the same time, perturbations from shifting moons may scatter ring material. Slowly, the rings could spread outward or fade into a thin, ghostly haze. Over eons, the resplendent bands will become a dim, ghostly smudge against the darkness. What becomes of a moon that slips free? Once untethered from its giant, a moon can become a tiny planet of its own. It may settle into a stable orbit around the star, tracing a lonely path in the cold. Alternatively, it might stray so far that it escapes entirely into interstellar space. Some moons could even be captured by another planet, changing allegiances. In all cases, life for these orphaned worlds is transformed. They no longer circle a massive parent, but roam as solitary remnants in the vastness of space. Their journey continues, but the comforting pull of their family is gone. For their part, even the mighty gas giants themselves begin to lose their fury. Over eons, the internal heat that powers their storms slowly leaks away. The great red spot on Jupiter, a raging storm for centuries, may slowly shrink and disappear as the planet cools. All across Jupiter and Saturn, the bright cloud bands will fade and dim. Without a strong internal engine to drive them, winds will decelerate and storms become gentler. Gradually the swirling colours dull. Where once belts and vortices roiled, now calm layers spread. The once dramatic storms of the giants will dwindle into nothing. Take Jupiter's great red spot, a tempest larger than Earth that has raged for centuries. In the cooling atmosphere, this storm would slowly shrink and fade, its ferocious circulation weakening to a gentle breeze before disappearing. Across the planet, the bright belts and dark zones would blur into one another as winds decelerate. Saturn's storms, once forming a great hexagon or periodic outbreaks, would calm into nearly uniform bands. Neptune's storms fade similarly. In time, each giant's face becomes a calm, uniform disk, a serene sphere marking the end of its wild weather. Even the outer giants of our system would slow down. Uranus, already a pale blue due to its calm atmosphere, would simply grow colder and darker, its features becoming even more subtle. Neptune's furious storms, dark spots and bright clouds, would lose their fury as well. The famous great dark spot would fade, and its billowing clouds would flatten. In time, both planets would display only gentle bands of cloud, hardly distinguishable against their icy cores. No storm would stir. These giants would appear as serene, monochrome spheres. As ages pass, the giants themselves become faint relics of the worlds they once were. If a distant observer were to approach one, they would find little more than a pale sphere. The dazzling bands and fierce storms of their youth have softened to muted tints and still patterns. Under the faint light of the dying star, their atmospheres reflect only a dim glow. The vibrant colours are gone, replaced by uniform greys and blues. Even a spacecraft venturing close would note a colder, less dynamic world. The giants carry no scars or memories on their surfaces, only silence. Their enormous masses remain, but they no longer churn with light. Jupiter's deep reds turn to oranges and browns, almost indistinguishable, and Saturn's yellows fade to pale white. Their magnetic fields weaken and their glows dim until they seem almost ordinary. Like ancient statues carved from gas, they stand motionless against the stars. These are cosmic tombstones marking an era that has passed, gentle reminders of the vigour that has now faded. These giants are the last flickers of an older time. In 1 billion years, Jupiter may cool enough that its own glow nearly vanishes, leaving only a faint outline. Saturn, Neptune, and Uranus, likewise, will grow nearly invisible in the darkness. To a distant observer, they would be almost indistinguishable from empty space. These planets are truly shadows of their former selves, carrying only the barest trace of the heat and light they once held. In the end, the last beacon of warmth will fade, leaving the cold quiet behind. When the star finally collapses into a white dwarf, the giants settle into their final orbits under a faint glow. This tiny stellar ember emits only a fraction of the heat it once did. The planets spin slowly, their days and nights governed by the weak light of the remnant star. Over time, they lose any remaining warmth, settling into a long sleep at temperatures of just tens of degrees above absolute zero. Hydrogen and helium in their envelopes grow incredibly cold. They may even coalesce into superfluid or metallic ices. The once gaseous atmospheres condense into slush around dense cores. In effect, each becomes a vast sphere of cold liquid and solid gas, barely distinguishable from a giant ice world. These frozen giants will linger as silent monuments for eons. Their dense cores stay intact, but everything else is like a field of ice. A distant future explorer might compare them to enormous comets, moving leisurely around a fading star. Over the longest timescales, they continue their slow orbits in near absolute darkness. Nothing new awakens. Their fate is to remain unchanged, still, and cold. Even the passage of time seems paused for them. In this endless winter of space, each gas giant is but a faint echo of the vibrant world it once was. Even these ancient giants are not guaranteed to remain forever. On cosmic timescales, even a faint nudge from a passing star or the galaxy's gravitational tides could eventually set them free. If their star continues to lose mass very slowly, the planets may drift even farther out. In some scenarios, they could escape altogether, joining the ranks of cold, wandering worlds between the stars. Until that distant fate, they endure in place, enormous spheres of ice in the silent night. Onward they travel, carrying the memory of stars long faded. In the vast darkness beyond their fading stars, the great gas giants begin a long, slow surrender to the cold. Over unimaginable eons, the heat that once roiled their interiors seeps quietly away. The great turbulent furnaces of their cores grow dim, glowing embers turning to memory. Without a steady inflow of energy from any star, they gradually give up their warmth to the void, losing more and more of their heat with each passing age. Even now, the giant planets draw a faint warmth from their own slow contraction. As gravity squeezes them ever so slightly tighter, it stirs heat in their depths. For much of their history, this Kelvin-Helmholtz effect has kept them warm like a dim fire. But in the distant future, that squeeze will all but cease. Even shrinking by a few extra centimeters each century yields only a ghost of heat. It buys time, but in the end, even that ember will go out. The cooling of a gas giant truly takes eons. Theoreticians estimate that after 1 trillion years, Jupiter's heat output might only fall by a few hundredfold, meaning it remains comparatively warm for a very long time. Its cooling clock is enormous, on the order of 10 to the 11th power years or more. In other words, even after what we think of as forever, a gas giant like Jupiter would still be radiating measurable heat into space, albeit much reduced. Inside giants like Jupiter, helium droplets constantly rain toward the core, releasing gravitational energy. This process gives the planet extra heat today, part of the reason it emits more energy than it gets. But eventually, the supply of helium wanes. When most of the helium has already settled deeper, this gentle heater will fade away too. Then yet another spark is lost to the cold. Compared to Earth, a gas giant holds very little in the way of radioactive heat sources. Without a substantial radioactive core, they have no internal nuclear furnace to continue warming their interior. Apart from initial formation heat and minor effects, there is no new energy to tap into. They rely on what remains from their birth and any minor internal processes. In this sense, once that is gone, nothing will light them again. Today, astronomers have measured its cooling. It shrinks by only a few centimeters each century and drops by about 1 degree Celsius every million years. At this rate, heat leaks away at a glacier's crawl across cosmic time. It would take billions of years of such gradual chilling for the planet to approach the frigid background temperature of space. As they cool further, the gas giants gradually change character. Hydrogen and helium, once fluid under tremendous heat and pressure, begin to behave like exotic ices of the far reaches. Hydrogen can condense into solid form, potentially creating a shell of floating ice. Helium, remarkably, stays liquid even near absolute zero under the crushing pressures within the planet. In effect, a gas giant in the long cold could become cloaked in an icy shell atop a dark liquid core, appearing solid while still harboring an unseen warmth deep below. Deep inside, any heavy element core also grows silent and cold. If Jupiter has a rock and ice core, it too would become a frozen lump of material. Once possibly molten or liquid under crushing pressure, that core would eventually lock up at near the background temperature. The concept of a core in these far future giants is almost philosophical, a stony or icy relic at the center of a vast frozen globe. In that final frigid future, even the atmosphere might freeze solid. The swirling clouds of ammonia and methane would cease their roiling motion. Gentle snowfall of frozen gases could drift over the once turbulent skies. The once raging storms and winds would fall completely silent, leaving a still, muted world. What was once a living, dynamic atmosphere becomes a quiet, ice-bound veneer on a dark globe, a husk of its former luminous self. Even the deep hum of weather would fade from a frozen giant. On Jupiter, powerful updrafts spawn lightning storms with flashes brighter than any on Earth. In the cold, still skies of the future, those thunderclouds would disappear. Without convection, there is no thunder or lightning at all. The planet's roar of wind falls silent. The only sound now is the echo of memory. If one could be there, one would feel only an uncanny calm, as if the world were at rest under a thick shroud of ice. In the hush of this cool, an even quieter change is underway in the skies themselves. All the wind and fury of a gas giant's atmosphere comes from its internal fires. Astronomers have watched continent-spanning storms erupt in Jupiter's skies, fueled by heat welling up from deep within. These storms dwarf anything on Earth, churning winds at speeds hundreds of kilometers per hour. Without that inner furnace, however, the storms cannot ignite. As the deep heat sinks, no new tempests form in the skies above. The clouds would cease their furious churn, and the entire sky would slowly steady. One can already see this process quietly unfolding on Jupiter. The Great Red Spot, a storm twice as wide as Earth, has been steadily shrinking for decades. Historical observations allow us to measure this waning. In 1879, it spanned about 39,000 kilometers. Today, it is only about 14,000 kilometers across. As it shrinks, its deep red color slowly fades and its shape grows rounder, a sign of energy lost. If current trends continue over millennia, this iconic vortex may vanish entirely, simply merging into the surrounding clouds. Even smaller storms drift away or merge with neighbors, and none take their place. Meanwhile, the giant's signature striped pattern begins to blur. The fierce jet streams that once zipped around the planet slow to a crawl. These powerful winds, driving alternating light and dark bands, have painted the sky with bold stripes for centuries. But as the atmosphere cools and the energy dissipates, those stripes soften. Boundaries between light and dark belts fade. The once bright colours may wash into a uniform grey. Eventually, the colourful belts might blend together into a dull, lifeless haze, as those once violent currents dissolve. Even the clouds themselves transform in the deep chill. Ammonia, methane, and water, once forming bright cloud layers, could begin to freeze or rain out of the upper atmosphere. The vivid white and coloured clouds might settle into an icy blanket. We could imagine the brilliant cloud tops fizzling as moisture freezes into tiny ice crystals and drifts down. In place of endless storms, there would be only calm, silent clouds. In every way, the planet grows still. The howling winds and thunderous storms fade away into silence. Where once violent weather roared, now there is only a tranquil, frozen quiet. The giant stands as if lulled to sleep, its once turbulent atmosphere serenely still. In effect, these worlds become silent monuments, the ghost of a living weather, only a memory. Even the ice giants, Neptune and Uranus, will fall silent in time. Their howling winds are driven by the heat within, and once that runs out, the winds slow to a whisper. Neptune's record-fast gales today would also see those storms fade with the cooling. In the end, all these distant giants share the same fate, silent stillness enveloping them. In the end, the heavy banded planets lie beneath eerily still skies. The roaring chorus of winds and storms falls away into silence. In this deep calm, the gas giants drift as silent beacons in the endless night, monuments to a once turbulent past. Their still forms now stand watch over the cosmos, silent sentinels of a weather long stilled. For untold eons, they will keep this quiet vigil, bearing the memory of the storms they once waged. And as the thunder of the skies fades away into history, the invisible shield of the world also weakens. Today, a Jupiter-like planet wears a tremendous magnetic shield. Jupiter's magnetosphere is immense, reaching millions of kilometers into space, larger than the planet itself. It is generated by electrical currents in its deep interior, where liquid metallic hydrogen flows under heat and pressure. This dynamo is powerful now because the planet still holds much energy. But in the long night, that driving power will flow down. Eventually, the generators of the field will slow and almost stop. As the giant cools, the convection that drives the dynamo will weaken. The currents of molten material that crank out the magnetic field will gradually slow. One can picture it like a generator running down. In fact, models suggest that a cooling gas giant's field strength falls off very slowly with time. At first, its once multipolar field might simplify into a more uniform dipole, but even that dipole grows weaker. Over billions of years, even Jupiter's staggering magnetism would fade to a fraction of its former power. Eventually, the magnetic shield almost collapses. The enormous bubble of charged particles around the planet would shrink closer to the world. The powerful radiation belts would weaken. Without that grand shield, the planet stands exposed to the galaxy's charged particles and cosmic rays. Any thin atmosphere that remains could be eroded by this space weather. The giant would become a lonely, bare object under relentless cosmic bombardment. In the end, even the invisible magnetic tapestry is torn down. The crackling auroras that once danced at the poles vanish. The radio roar of its magnetosphere, heard by passing probes, dwindles into nothing. Even this last ghost of motion fades, leaving only a whisper of magnetism behind. It is a bit like Earth's magnetism billions of years from now, if its core cools completely. Mars, once active, now has no global field at all. Gas giants, enormous as they are, follow the same universal script in time. Even brown dwarfs, heavier cousins, see their own fields decay. Scale is different, but the fate is the same. Once the dynamo stops, the magnetic glow dies. We should note that this magnetic destiny is shared by all giants, including the ice giants. Even now, Uranus and Neptune have unusual magnetic fields tilted far from their poles. But as they cool, those too will fade away. Uranus's decentered field and Neptune's multipolar field rely on warm, conductive layers. In the dim future, those layers will cool to the point where even their peculiar fields can no longer be sustained. Another way to see this is by thinking about energy. The magnetic field taps the planet's internal heat as its source. As that heat bleeds away, there is simply less energy to power the magnetosphere. It's similar to how a slowly dying engine sputters before stopping. At first, the magnetosphere may persist for ages, but become feebler each time. Eventually, without a sustained engine inside, even that faint whisper of magnetism will vanish. And some giants, after cooling and fading, are cast free of their stars, left to wander alone into the galaxy. Not all gas giants remain tethered to a star. In some systems, chaotic gravitational encounters will fling a giant into the abyss. If two massive planets pass too close, one can sling the other outward at escape velocity. Even the star's final breath can hurl a world free. If a dying star sheds more than half its mass suddenly, its outer planets can drift away on new, unbound trajectories. In such cases, a gas giant becomes a castaway, hurled alone into interstellar space. As a lonely wanderer between the stars, a gas giant is completely cut off from any sun's warmth. It drifts in the darkness, carrying only the heat left inside it at the time of its ejection. Astronomers have detected such objects. Surveys of the sky have turned up a number of rogue planets, objects as large as Jupiter with no star to light them. One famous example is WISE 0855-0714, a planetary mass object only about 7 light-years away, with an estimated temperature around 250 Kelvin. Even at that balmy-sounding 250 Kelvin, it is far warmer than the giant would otherwise be in deep space, and it still glows only with its own ember-like heat. In the vast cold of space, without sunlight, a castaway giant planet will eventually cool just as the anchored ones do. It will radiate its heat into the cosmic background, slowly darkening. Yet the processes are familiar. Its atmosphere will grow still. Its magnetic dynamo will fade. Unlike its siblings around stars, this lone wanderer feels only the emptiness of space and rare cosmic rays. it slowly joins the ranks of interstellar nomads, silent and frozen. In fact, microlensing surveys suggest there may be at least as many free-floating Jupiter-sized planets as there are stars. These lonely giants drift through the Milky Way, mostly unseen. In the deepest cold, they glow only faintly with the last of their heat. Over immense ages, each one becomes a frozen monument drifting in the galaxy's night. Imagine one of these giants in interstellar space. It has no sunrise or sunset, only the faint glow of distant stars to light its days. Its sky is the black depths, and its illumination comes only from the remnant heat within. At tens of kelvins, it is far colder than any planet near a sun. To our telescopes, it appears as a tiny, ultra-cold dot in the infrared. The cosmic microwave background bathes it at a few kelvins, a faint afterglow of the Big Bang. If the galaxy ages still, even that radiation will cool, leaving the wanderer in almost absolute darkness. Some of these drifters may eventually find a new home. If a rogue planet passes near another star, it could be captured by its gravity and become a new planet in that system. Otherwise, most will wander the galaxy to the end of time. Even then, they serve as monuments to their birth systems, carrying the memory of lost suns in their icy depths. Others, however, continue orbiting their sun's remains, surviving stellar death. After a star like the Sun burns out, its remaining core is a white dwarf, a faint, cooling ember. In that aftermath, an outer giant that was once warmed by a bright sun may instead orbit under a perpetual twilight. Our own Jupiter, for example, is expected to remain bound to the Sun when it becomes a white dwarf. Stripped of most of the Sun's mass, Jupiter's orbit will expand, perhaps doubling in size, which should keep it safe from engulfment. It will circle the remnant star under a twilight sky that is far dimmer than it used to be. Astronomers have now found examples of such survivors. In 2020, the discovery of WD 1856 plus 534b confirmed a gas giant orbiting a white dwarf. This world is roughly 6 times the mass of Jupiter and sits in a close orbit, but it receives almost no heat from its small star. Observations show its temperature is only about 186 Kelvin, making it the coldest exoplanet measured so far. It orbits in a kind of endless dusk, bathed in the weak glow of the white dwarf's light. These surviving giants experience extreme conditions. With little stellar light, their atmospheres are frigid, even if they retain internal warmth. If they had any radiative glow, it comes from their own stored heat, not the star. Their skies would be forever dark, punctuated only by faint starlight. On the bright side, they no longer face the fierce winds of stellar radiation. The fate of inner giants may differ. Some close planets could be engulfed or evaporated when the star ballooned up, but a massive outer world is safer. If it survives the fiery expansion, it will settle into a new orbit in the white dwarf phase. Even then, it may be perturbed by remaining debris or surviving companions. For example, WD 1856 plus 534b may have drifted inward after its star shed mass. In any case, these giants live on in the cold glow of the remnant star, circling quietly in the aftermath. For countless years, these twilight giants circle quietly. Over time, the white dwarf itself will cool and fade, and the planets grow colder still. With little external influence, they continue to cool on their own, and their feeble magnetism fades away. In the end, they become much like the distant frozen giants we described earlier, silent and cold, but still bearing the memory of the light and storms they once knew. The sky over a giant orbiting a white dwarf would be eerily muted. The remnant star's light is so feeble that the planet might be enveloped in perpetual twilight. Softly glowing clouds could reflect that ghostly starlight, turning the heavens a pale lavender or blue. There would be no sunrise or sunset. Instead, one constant half-light, punctuated only by the twinkle of distant stars. Getting to this fate is often tumultuous. During the star's red giant phase, the system becomes violent. Inner planets vaporize and debris sweeps through space. A surviving giant could plow through this debris or fling it away. Tidal forces and drag with leftover gas might change its orbit. In some cases, an old moon or disk could deposit dust into its atmosphere. In short, any planet that remains has weathered a stormy end to its star's life before settling into a quiet new order. Eventually, the white dwarf itself will cool to near invisibility. The gas giant's sky will turn even darker, closer to the frozen black of interstellar space. With no stellar heat, its only glow is from internal energy or passing starlight. Over unimaginable ages, it fades to join the galaxy's coldest shadows. Even now, these twilight worlds remind us that planetary stories can stretch far beyond the life of any star. Whether bound or wandering, in the end, all these giants converge upon the same final destiny. In the end, each gas giant becomes a quiet throne of ice. Stripped of warmth and storm, it persists as a vast frozen orb. It is a huge sphere, mostly made of hydrogen and helium, but at such low temperature that even those gases are solid or liquid. Even its possible rock or ice core is locked in icy stillness. To any observer, it now seems static and inert, radiating almost no light of its own. These giants may still orbit or wander, but in either case, they stand alone. If bound to a star remnant, they circle ever more slowly. If set adrift, they journey through darkness without aim. Regardless, they survive longer than nearly any other world around them. When stars have vanished and galaxies settled, these frozen behemoths will remain, ticking on their own slow cooling. Truly, they become some of the oldest witnesses in the cosmos. In the universe's last light, these silent worlds are monuments to much older ages. They carry within them the primordial gas and materials of their birth systems. Their bulk chemical compositions, formed in the ancient protoplanetary disks, are preserved for eons. As relics of a fiery youth, they tell a story no other object can. In their quiet endurance, they seem like thrones, silently awaiting the last page of the cosmic story. With all energy spent, they are serene guardians of their long-dead family of planets. The galaxies may change, stars may come and go, but these giants, inert, frozen, yet majestic, remain. Even as the universe cools around them, they sit as icy citadels of time, watching the last ages unfold. For eons beyond human timescales, these frozen giants endure. Even when their host stars and any trace of life are gone, the planets themselves persist. They have no sky to illuminate or life to sustain, but the fabric of themselves remains. In fact, when the galaxy's last light fades and black dwarf stars roam, these planets will still silently spin in the dark. They are the final holdouts against cosmic oblivion, carrying their ancient essence into the farthest future. As the final embers of stars fade, roaming giants drift through the ever-expanding darkness. With no sun to warm them, these solitary worlds carry their own cold light, on silent journeys across the void. In the vast loneliness beyond galaxies, they travel slowly, unhurried and immense. Far from the warmth of any star, their massive bodies cool quietly, radiating what heat they have into the emptiness. They glide through interstellar space like ancient vessels, relics of a once vibrant cosmos. In the far future, even the cosmic background radiation will dim, and these giants will share the darkness of space. As the universe grows colder still, these giant planets will become nearly indistinguishable from the night around them. As the distant future unfolds, these colossal planets become denizens of a pitch-black realm. Imagine one of these giants floating at the edge of a galaxy cluster, with no nearby stars to light its skies. Instead of storms lit by sunrises, it is shrouded in perpetual twilight, where even twilight is barely a glow on the horizon. The planet's atmosphere, once vibrant with colours and bands of gas, settles into an endless, frozen hush. The swirling clouds of ammonia and methane that once dazzled observers are now locked in place, hanging like ghostly curtains. This world drifts like a grand ship on an endless sea of emptiness, its white polar caps growing as the deep night approaches. Over unimaginable eons, as stars burn through their fuel and fade away, the universe itself cools. New stars will cease to form, and the familiar constellations will vanish. The cosmic microwave background will dim, and even leftover starlight will be a faint whisper against the dark. In this deep future, gas giants drift in silence, their atmospheres slowly releasing the last of their heat into the void. Without any sun to nourish them, their skies grow darker, their hearts of gas growing denser and more still with time. Over the course of 1 trillion years, even the mighty heat engines inside these worlds will exhaust themselves, rendering them nearly as cold as the surrounding space. They become quiet, cold shadow worlds, almost indistinguishable from the infinite darkness that surrounds them. In such emptiness, these giants become ancient monuments to a bygone era, their presence felt only by the faintest gravitational pulse. Even a wandering photon might never meet their surface as it glides by. And yet, they linger there, massive and solitary, turning slowly in the unending night. These frozen giants remain as silent testaments to the ancient fires of creation that have long since faded from the cosmos. Time itself almost seems to pause around these giants. For ages unimaginable, billions upon trillions of years, they drift virtually unchanged. In an era where even the faint glow of the cosmic background has nearly vanished, they persist as silent anchors to history. Every second is slow and deep. An hour might stretch across eons of human time. By then, even the brightest star has long since become a fading ember, and galaxies themselves are dark silhouettes. Yet, the giant planet will still turn, patiently and imperceptibly, in its lonely voyage through the void. Every moment is slow and deep. A single day could stretch across eons of human time. By then, atoms themselves will have started breaking down under the relentless passage of time, yet the giant planet will still turn, patiently and imperceptibly, in its lonely orbit through the void. Each planet holds memories of a star that once was, its core still warm with ancient energy that slowly wanes. Time, to a drifting planet, has grown almost infinite. Deep within these ancient planets, an even slower drama unfolds. The heat from their violent formation and subtle radioactive processes quietly dissipates. For an extended time, the core remains warmer than the surface, shedding heat outward through the thick atmosphere. But with no new energy to replenish it, even the core will eventually cool to the ambient temperature. In 1 trillion or more years, the entire world could become nearly a uniform frozen mass, with temperature differences as slight as the faintest whisper of warmth. Without any source of heat, the thermal gradient across the planet fades, leaving a world that is nearly isothermal. In this final state, the planet itself might become a colossal ice ball floating through darkness. It is a scene of serene stillness. The giants drift silently, enshrouded in perpetual dusk. Like gigantic icebergs adrift in an endless ocean of emptiness, they mark the passage of cosmic time. Even light itself has little to say. Any starlight or relic radiation is barely a faint murmur here. Only the echoes of ancient heat remain, slowly fading into the ether, until one day these giants themselves will share the darkness of everything around them, indistinguishable from the starless void that holds them. In their profound stillness, they become storytellers of the cosmos, their silence whispering secrets of ages past. These worlds know no sunrise or sunset, only an endless night. Without a nearby star, the concept of day fades away. Any light would come only from distant galaxies, tiny pinpricks in the dark. The planet itself could only glow faintly, if at all, from any residual heat it retains. For any watcher on its cloud tops, the sky is as dark as the void of space all around. Time on these worlds is not measured by orbits around a sun, but by the slow wobble of planets in space, or by the ticks of the universe itself. What remains of these giants is a story of survival. They are the last breaths of planetary science in a dying universe. Their existence is fleeting in a cosmic sense, but for a time they hold together the physics of worlds. In the silent night they endure. Their sheer scale is astonishing. Even shrouded in ice, each still spans distances greater than the orbit of Earth around the Sun. They remind us that even as stars fade, vast structures persist, unchanged except by the slow hand of entropy. In this way, they stand as silent guardians against total oblivion. But even in this deep cold, these giant planets do not always travel in complete solitude. Over cosmic timescales, their quiet journeys occasionally intersect with other wandering objects. Two massive worlds, each 1,000 times the mass of Earth, might cross paths in the dark, slowly drawn together by gravity. In the silent void, collisions happen with almost no warning. When a great gas giant meets another, they may merge into an even more enormous world or send shockwaves rippling through each other's atmospheres. The crashes are slow and immense, like two slow-motion comets colliding with the weight of oceans. The result is a sudden reordering of their destinies in the silent night. Some gas giants wander so near that one can capture a smaller companion, turning it into a new icy moon. Gravity's pull can slowly snare stray comets or asteroids, adding to the giant's entourage through the ages. Even whole worlds, stripped of their stars, can become satellites of these behemoths in a slow gravitational dance. Slow gravitational tides pull a wandering rocky world or ice chunk into a new moon orbit. Over time, a planet can accumulate these companions, ancient asteroids, captured dwarf worlds, or stray ice balls, building a ghostly entourage. These new moons, frozen and cold, circle their master in long, slow orbits, testament to the patience of gravity. Sometimes, even the giant's own ring system can capture objects, increasing the dance of debris. Long ago, our own Jupiter and Saturn may have done the same in their stars' brighter days, a pattern that now plays out in eternal night. Often, though, these giants wander completely alone. Over eons, they are carried by the slow currents of gravity and cosmic expansion to the far reaches of their galaxy, or even into intergalactic space. In these lonely stretches, encounters become exceedingly rare. A giant planet might spend countless ages drifting in complete solitude. Undisturbed, it sails the cosmic sea of emptiness, never meeting another object to break the silence. Alone, it drifts through endless darkness, a solitary ship on an unfathomable ocean of stars that no longer shine. In that stillness, the planet slowly becomes one with the void, a silent voyager of the eternal night. Even time seems to forget it, as the quiet giant sails on unchanged through the cosmic darkness. Occasionally, even a single encounter can change a world's course. A wandering giant might pass near an old star or stellar remnant and be captured into a new orbit. For example, a lone white dwarf or brown dwarf could catch the planet in its gravity. With time, the gas giant would settle into this new orbit, perhaps warmed, however faintly, by its dim new master. The captured planet might brighten slightly, its atmosphere shimmering with the leftover heat of a long-distant sunrise. This drawn-out embrace could give the planet a second life, illuminated by the ghostly glow of a dying star. Such rare encounters can turn solitude into companionship, however brief, in the endless expanse of space. In some corners of the universe, encounters might be more common. Within dense star clusters or the packed centers of galaxies, even wayward planets are not entirely alone. Gravity can shepherd groups of remnants, and wandering giants might accidentally join these drifting families. In such crowded backwaters, collisions or captures could happen with surprising frequency on cosmic timescales. Even the loneliest planet might find fellow ghosts of worlds, adding unexpected chapters to its silent journey. It's in these bustling cosmic neighborhoods that a solitary wanderer may find, for once, the company of another. Imagine, if you will, these giants like ships at sea in a night without stars. Sometimes, guided by unseen currents of gravity, they may brush past each other or even collide head-on. Other times, one might quietly pull another into tow, like one ship taking another in its slipstream. In other cases, they remain oblivious of each other's presence, each wandering its own course. Over trillions of years, even these improbable interactions shape their fates, carving out new stories in the void. In a collision, the result can be breathtaking. Picture two planets meeting. Their atmospheres churn and intermingle, releasing long-suppressed heat in explosive bursts. The dark is briefly illuminated by storms and lightning, as energies long trapped now surge. Over months of slow-motion fury, they may settle into a new equilibrium, a larger planet reborn from the two, or break apart into a cloud that eventually cools into new bodies. Such an encounter writes a dramatic chapter in the lifelines of both worlds, even if it unfolds in a silent, slow-motion ballet. In the aftermath, a collision can leave behind dazzling structures. New rings of debris may form around the merged planet, each speck of ice tracing an orbit for eons. Captured fragments can become permanent fixtures, new moons born of destruction. These new moons, frozen and cold, circle their master in long, slow orbits, testament to the patience of gravity. Each ring and moon carries the scars of the impact, circling forever as reminders of that cataclysm. Thus, what begins as chaos gradually settles into a new order, even as the universe itself continues to drift quietly onward. In the grand tapestry of the galaxy, these drifting planets may sometimes trace out gentle patterns. They might follow the curves dictated by the galaxy's gravitational contours or the ghostly map of dark matter. At times, a few may even end up traveling in the same general direction, like a spaced-out convoy with no destination. They share nothing but a common corridor through space, not bound to each other by gravity, but by the subtle structure of the universe itself. Such alignments are fleeting, yet they hint at the cosmic web that holds all matter, even in the darkest reaches. Over unimaginable timescales, the composition of these giants slowly changes. Their atmospheres, once boiling with gas and storms, begin to settle into icy stillness. In the intense cold, hydrogen itself can solidify, forming vast seas of frozen molecules. Deep inside, helium, long reluctant to combine with hydrogen, starts to condense. Giant droplets of helium might rain through the atmosphere, pooling in the depths. As the millennia pass, even this liquid helium will eventually freeze, solidifying layer by layer from the top downward. Far from the heat of any star, these transformations unfold at a glacial pace. In the vast, cold hydrogen gas begins to form crystalline structures, like a great snowball forming in reverse. Helium, which resisted freezing on these giants for ages, finally succumbs, first as dense droplets and later as a solid shell. Even deep inside, pressures remain high enough that exotic phases may linger. Over unimaginable eons, layers of frozen hydrogen and helium build up, turning the once swirling atmosphere into a rigid crust. The whole world gradually transforms, evolving from a raging storm of gas into a slow-moving ice giant, harboring a solid heart beneath its frozen exterior. Over time, the planet builds up enormous stratified layers of frozen gases, each as smooth and solid as the facade of an interstellar cathedral. In this unimaginable cold, hydrogen itself begins to freeze. The gas that once roiled in perpetual storms starts to settle into crystalline structures. At first, tiny ice grains form deep in the atmosphere, slowly falling like snowflakes, though 1,000,000 times larger. Each crystal is minute, but over eons, the process continues, layer by layer, gradually coating the planet in an icy glaze. It is a universe of slow motion, snowflakes of hydrogen that take centuries to drift from sky to surface. In this way, the outer envelope of the planet turns from a cloudy mist into an ice-bound shell, solid at last in the long night. Helium, the second lightest element, resists freezing much longer than hydrogen. Yet in the endless cold, even helium can no longer remain fully fluid. Huge droplets of liquid helium may form deep in the atmosphere, slowly coalescing before freezing solid as they fall. These pockets eventually freeze too, adding a layer of crystalline helium ice on top. Meanwhile, in the deepest interior, hydrogen may remain in an exotic metallic form under immense pressure, but even that could eventually solidify into a strange, ultra-dense crystal lattice. Over tens of trillions of years, the planet builds up enormous stratified layers of frozen gases, each as smooth and solid as a diamond wall. In this way, the giant planet's once vast atmosphere is transformed into an icy, impenetrable shell. The result is an astonishing transformation. What was once a roiling gas giant becomes something more akin to a frozen ice world, vast and silent. Under its night sky, even the smallest star would shine dimly, barely warming its crust. In the cold void, the planet's rotation is a slow, deliberate spin, each day lasting longer as the atmosphere thickens and slows. It might look like a giant comet, slow-moving, quietly reflecting the faint radiation that ever reaches it. In this form, it becomes almost like a relic, an enormous, dark, frozen sphere slowly traversing the emptiness. The once vibrant bands and storms are replaced by still plains of ice, and any motion is so gradual as to be imperceptible. It's not just the gases. The interior may become equally frozen. The deep rock core, if there was one, cools until it too is as cold as the surrounding layers. If there were storms, they end. If there were winds, they become still. What remains is an icy colossus, its secrets locked beneath layers of frosty gas. Under the right conditions, even chemical reactions halt, leaving a chemically static world. In every sense, the planet enters a state of hibernation, as much alive as a statue made of winter's heart. In the end, even the fire inside the world goes out, leaving nothing but an unbroken silence. Yet change can still come, albeit slowly. If the planet drifts through a dense gas cloud, it may accrete new material, adding layers of exotic ices on top. Conversely, a faint warming from a distant star or cosmic event might create a brief, gentle thaw in its crust. Even these tiny changes leave their mark. The ice shell could wrinkle or fracture, creating new frozen terrain. Over unimaginable spans, these small processes continue to write subtle new chapters in the planet's frozen history. Though imperceptible in the moment, each new grain or crack is a reminder that even on the edge of time, the universe continues to evolve. Even stranger things may occur under those extreme pressures and low temperatures. Methane in the atmosphere could break down, releasing carbon that crystallizes into diamond flakes, raining deep into the core. In this sense, the planet's interior becomes a trove of jewels, diamonds on scales beyond comprehension. Perhaps oxygen would form ice, and exotic ices of other elements would line the interior walls. Over unimaginable eons, the world would become not only cold, but fantastically crystalline, an interstellar jewel of ice and gem hidden in eternal frost. From the outside it looks cold and dark, but within lies a bizarre cathedral of physics and chemistry. In these exotic conditions, even familiar elements behave strangely. Helium might flow as a superfluid deep in the gas giant's heart before finally joining the solid layers. The physics of such a world would be bizarre. An ocean of liquid metals above a core of solid hydrogen, all under an icy crust. Yet to any observer, it is simply a silent, cold planet, indistinguishable in darkness from any other. But within, it holds the strange beauty of physics stretched to its limits. It becomes a world where the rules bend and familiar substances form alien landscapes of crystal. Not all giants behave exactly the same. Smaller ice giants, with more water and ammonia in their makeup, could freeze differently than a true gas giant like Jupiter. Uranus and Neptune, for instance, may become solid sooner because their composition is richer in heavier ices. Meanwhile, a larger giant with a high percentage of hydrogen might take longer to fully crystallize. Each world's unique mix of elements dictates its own path through the freeze, but all share the same destiny of becoming icy husks in the cosmic winter. In the end, whether big or small, each frozen world becomes a monument to the relentless cold. Beyond hydrogen and helium, other elements find new forms too. Methane might break down, leaving carbon to form diamond ice. Ammonia could crystallize into nitrogen and hydrogen compounds. Even rock might metamorphose under crushing cold and pressure, forming high-pressure ices of silicates. The final planet could be layered in a way utterly alien to a warm world, each stratum a record of chemistry in deep freeze. Each layer is a chapter in a frozen history, from the hydrogen frost at the top to the silicate core below. This is a world sculpted by time and chill into a quiet masterpiece of ice. Of course, this transformation takes place on inconceivable timescales. Today's gas giants, warmed by stars, have atmospheric temperatures above hundreds of degrees, but in the dark future, they will cool to just a few degrees above absolute zero. Only when the temperature in their outer layers falls to around a dozen kelvins will hydrogen ice begin to form. This slow cooling might not happen until trillions upon trillions of years have passed. In that endless stretch of time, even the laws of physics proceed in whispers, sculpting the planet into its final, crystalline form. The universe itself, extending into infinity, provides a backdrop where time has nearly no meaning and transformation is almost imperceptible. Approaching a black hole, the very fabric of space begins to curve under the planet's feet. Tidal forces, the difference in gravity between the near side and the far side, become enormous. The side of the planet closer to the black hole feels a much stronger pull, stretching the world into a long, slender shape. It starts as a gentle elongation, but as the giant moves closer, the pull grows stronger, and its own gravity can no longer hold it together. In a dramatic display, the planet distorts into a long thread of rock and ice. Beyond a certain critical distance, known as the Roche limit, the disruption becomes irreversible. From a safe distance, one might see a streaming ribbon of vapor and debris extending from the giant toward the black hole, a glowing tendril pulled from its body. A neutron star can inflict similar devastation. In the grip of its intense gravity, a passing planet can be torn apart much like before. Unlike a black hole, a neutron star has a surface, so the fragments may impact that surface or form a dense ring around it. In either case, the encounter is violent. Material from the planet might ionize and emit a brief flash of X-rays before spreading into space. The once stable giant is broken, its remnants cast about as cosmic debris, forever changed by its dark encounter. Even white dwarfs and other dense remnants can tear a planet apart in this way. The colossal gravity of any compact star leaves little chance for survival. Even a glancing encounter can leave its mark. A planet passing just beyond the Roche limit may not fully disintegrate, but its outer layers still tear away. Strips of gas and ice spiral outward, forming arcs and clouds of debris trailing behind. Over successive orbits, each close pass strips more material, gradually weakening the planet. In some cases, the planet might end up on an eccentric orbit, losing more mass with each lap. It is a slow destruction, written in arcs of debris against the starry sky. The planet's fate is sealed over many millennia, patiently unraveling into space as it continues its doomed orbit. Eventually, even the iron core of the giant may be at risk. If it is massive enough, it could survive the initial shredding, only to be whittled down over time. As the galaxy itself changes, perhaps the black hole fades or moves, and the core is left floating free, just a tiny remnant of its former majesty. But such survivors are rare. Oftentimes, nothing remains except the echoes of what once was. In many cases, the giant is reduced to a cold, silent spread of debris scattered across space and waiting to be forgotten. For any observers far away, the tidal shredding might produce a fleeting spectacle. As gas spirals into the black hole or neutron star, it can heat up and radiate energy. In the case of a black hole, much of the infalling material could emit powerful X-rays or gamma rays, producing a sudden flash in the darkness. For a neutron star, the fragments might crash onto its surface, igniting brilliant bursts of light. The shredded planet's remains can briefly shine brilliantly as they release gravitational energy, a final fireworks display marking its end. But once it fades, all that is left is a field of cold debris in the silent blackness. Each broken giant is a stark reminder of the impermanence of cosmic structures. Even a world of such size and power is fragile when faced with the extreme gravity of a compact star. The slow-growing crack, the stretching and eventual tear are testament to forces far beyond our daily experience. It is a cosmic drama of strength and vulnerability, played out on scales that dwarf any human story. In the aftermath, the field of debris is a silent memorial to that event, a testament written not in stone, but in orbits and ice. The giants' memories linger in the patterns of their remains. After a giant breaks apart, its debris can behave like a colossal asteroid belt. Each piece drifts on its own orbit, much like comets and asteroids around a star. Some fragments might even take on comet-like tails if heated, trailing wispy trails of gas as they move. Over time, this field of debris could thin out, but initially it resembles a graveyard of worlds, each fragment bearing scars of its origin. To any future observer passing through, it would appear as a cloud of ice and rock drifting silently in space, a ghostly halo marking the giant's last vestige. Under some conditions, even the shattered fragments have a future. If two chunks drift together, they might stick to form a small new world. In time, gravity could pull some of the debris into clumps, essentially forming a tiny planetary system out of the ruins. Thus, in the destruction of one enormous planet, many smaller worlds could be born, each with its own new story to tell. Even out of that violent end, creation finds a way to continue. In this way, the death of a giant can become the genesis of many smaller lives in the cosmos. Eventually, these frozen giants become true monuments to the void. In the complete darkness, without even starlight, they are virtually invisible. Floating in the emptiness, they cast no reflection and emit no light of their own. Only their faint gravity betrays them, quietly tugging on any matter that wanders too close. Drifting far from any star or galaxy, they are islands of ice and metal, unseen and undisturbed. These silent relics carry the memory of stars and worlds long faded, ghostly witnesses to cosmic history. In the vast emptiness, these giants appear as silhouettes against nothingness. To any wanderer from another world, they would be invisible, blending into the dark canvas of space. Even a journey of light could pass them by unknowingly, as they emit no light of their own. In such solitude, they become like ghosts of planets, eternal and unseen, silent reminders of what once was. Only a gentle thaw from a drifting star or an encounter with an energetic event could ever give away their presence. Even though they drift unseen, these giants remain monuments in an empty cosmos. Given enough time, they may collide with nothing, remaining intact longer than nearly anything else. If one could record the history of the universe, these silent wanderers would outlive many catastrophes, quietly preserving ancient secrets. They remind us that even in darkness, there are guardians of memory, holding stories from a distant past. In the heart of oblivion, they are statues of eternity, unobserved but ever present. Most of the time, these frozen giants remain invisible. Without starlight of their own, they cannot be seen by even the most sensitive telescopes. Astronomers might only spot them by chance, such as when they pass in front of a distant star, causing a tiny gravitational lensing effect. But in the vast emptiness between galaxies, such alignments are exceedingly rare. As a result, these silent monuments drift like secrets, present but undetected, hidden in plain sight. Only their gravitational footprints might reveal them, nudging dust or tiny rocks into motion where no light is found. Each frozen giant drifts under gravity alone, with no sun to call home. They wander in the gravitational field of their galaxy or cluster, often slowly spiraling toward denser regions. Some may orbit the center of a galaxy cluster, caught in its pull, but still unseen. Others could float completely free, moving through the void between clusters, with only the cosmic background as companion. Either way, they remain solitary, ghostly wanderers in the dark, perceived only by the faint tug of their gravity. In some ways, these giants become time capsules of the cosmos. They contain within them the original composition of their birth, primordial hydrogen and helium, along with heavier elements forged in long-dead stars. If we could one day find and study one, it would reveal the secrets of long-vanished suns. But for now, they remain out of reach, monuments to times and places long gone. Each silent wanderer stands as a guardian of memory, bearing witness to eras when galaxies were young and stars burned bright. Some of these wandering worlds might already be known to us. Astronomers have detected what they think are free-floating planets through gravitational microlensing and other subtle methods. These discoveries suggest that planets can indeed survive without a star, far into the galactic depths. Yet the ones we detect today are still young in cosmic terms. The relic giants of the far future would be even more elusive. What we see now may be mere infants compared to the ancient behemoths that will one day drift alone in space. For any observer on such a world, the night sky would be utterly black. No sun would ever rise, and no stars would ever twinkle overhead. Only the faint glow of distant galaxies, unimaginably far away, would hint at the existence of light. It would feel like endless midnight, with no beginning or end, and the gravity of the world would be the sole companion. In that silent darkness, the planet itself is both a refuge and a prison, a lonely witness to a universe long past its glory days. The very existence of these invisible giants is humbling. It reminds us of how much of the cosmos lies unseen and unknown. For every star we see, there may be countless dark worlds nearby that carry their secrets silently. These hidden giants could be as numerous as the stars once were, spreading the relics of solar systems across the dark. Their invisibility makes them both mysterious and poignant, monuments to the vastness that cannot be fully observed. One day, perhaps, advanced observers may discover these ghosts. They might search the skies for faint infrared glows or tiny gravitational tugs. Space telescopes might detect the faintest heat radiating from the planet's cores. Eventually, these unseen giants may reveal themselves not by light, but by the shadows they cast or the wobbles they cause. In that moment, a dark wanderer would emerge from anonymity, telling its tale of lonely drift to whoever is listening. In a sense, these invisible giants highlight a key truth of astronomy. Absence of evidence is not evidence of absence. Just because we can't see them with our eyes or telescopes doesn't mean they're not there, drifting quietly. Their existence reminds us that the cosmos is full of secrets, and we must keep looking for subtle signs. Imagine a future explorer saying, "I once saw nothing but dark space and discovered a giant world hiding there." These ghosts urge us on, suggesting that our instruments may always be just shy of revealing the universe's hidden depths. These frozen giants are monuments not just to bygone stars, but to the limits of our perception. If no one ever finds them, their stories could remain forever untold. Yet they exist all the same, awaiting discovery. In that way, they challenge us to expand our knowledge and to never assume we've seen all there is to see. They are beacons for future discovery, though their light is beyond our reach. In the final chapters of cosmic time, even these silent giants may face slow disintegration. Tiny but persistent forces gradually erode them. Microscopic impacts from rare interstellar dust and particles chip away at their frozen surfaces over endless years. Cosmic rays and radiation peel away atoms one by one from the ice and metal. Slowly, imperceptibly, the solid planet loses mass and structure. Even slight gravitational tugs from passing masses can nudge fragments off course, sending bits drifting into new orbits. Over unimaginable spans, this process continues. Over vast spans, these fragments drift even further from one another. In an ever-expanding universe, gravity becomes too weak to pull them back together, so they disperse through the cosmic web. Eventually, each shard becomes isolated from even its closest kin, a lone piece of ice adrift in emptiness. They follow silent, separate paths, carried along by the expansion of space itself. These frozen husks scatter into the silence, their fates forever set. In that endless dark, each piece travels alone, a tiny monument to a world that once was. Each individual fragment may face its own gradual end. If left undisturbed, fragments can eventually break into smaller pieces under tiny stresses or impacts. A shard of ice could slowly sublimate away, and any rock could be shattered by infrequent collisions. Over time, these pieces too would split into ever finer debris, until they become little more than cosmic dust, or even isolated atoms. By that point, the original giant has truly dissolved into the fabric of the universe. In a sense, the world lives on in innumerable grains scattered across the cosmos. In the grandest scope, these final fragments are just another phase in cosmic evolution. They drift in darkness, quiet and almost forgotten. Even their existence, once separate from their origin, becomes fleeting against the backdrop of eternity. As the cosmos marches on, they become little more than grains in the sands of space, each carrying a whisper of the giant it once was. Their story, like that of everything else, continues ever onward, deep into the vast emptiness beyond. The fragments follow the universe's flow, part of the never-ending journey of matter. Over inconceivably long times, even minute forces can play a role in their fate. High-energy particles from the background or occasional cosmic rays can erode their surfaces, knocking atoms loose. Each tiny impact chips away imperceptibly at the ice and rock. Cosmic radiation, though sparse in the emptiest depths, continuously bombards these fragments, altering their chemistry over eons. What seems eternal slowly wears down. Ultimately, each fragment carries scars of cosmic processes, every atom a testament to time. Over vast spans, these fragments drift even further from one another. In an ever-expanding universe, they move away from any nearby cluster where they might have once been. Gravity becomes too weak to pull them back, so they disperse through the cosmic web. Eventually, each shard becomes isolated from even its closest kin, a lone piece of ice adrift in emptiness. They follow silent, separate paths, carried along by the expansion of space itself. These frozen husks scatter into the silence, their fates forever set. Each individual fragment may face its own gradual end. If left undisturbed, fragments can eventually break into smaller pieces under tiny stresses or impacts. A shard of ice could slowly sublimate away, and any rock could be shattered by infrequent collisions. Over time, these pieces too would split into ever finer debris until they become little more than cosmic dust or even isolated atoms. By that point, the original giant has truly dissolved into the fabric of the universe. Even in fragmentation, the planet's legacy continues in these pieces. In the grandest scope, these final fragments are just another phase in cosmic evolution. They drift in darkness, quiet, and almost forgotten. Even their existence, once separate from their origin, becomes fleeting against the backdrop of eternity. As the cosmos marches on, they become little more than grains in the sands of space, each carrying a whisper of the giant it once was. Their story, like that of everything else, continues ever onward, deep into the vast emptiness beyond. Even as individual worlds end, the larger story of the universe unfolds without a final page. Over incomprehensible spans, even the atoms in these fragments could fade. Some theories suggest that in the far future, protons themselves might decay, dissolving matter into pure energy. If that happens, then even the last fragments would eventually disappear entirely, leaving only a faint hum in the fabric of reality. But on scales we can imagine, they end up as cosmic dust, a distribution of particles so sparse they barely interact. In that final state, it becomes almost philosophical. These fragments are at once gone, and yet etched into the memory of the universe. They represent the quiet, lingering aftermath of cosmic grandeur. Ultimately, the fate of these fragments merges with the fate of the universe itself. If protons decay in the far future, even atoms will dissolve, leaving behind only radiation. Perhaps even black holes have evaporated by then, and the last matter is gone. In that final stage, nothing truly remains in the void. No giants, no fragments, just energy spread thin. But until that ultimate end, these remnants continue their infinite voyage. Their legacy is the memory they carry, chapters of a story that stretches beyond our knowing, drifting onward through eternal night. As our journey through the cosmos carries us onward, a profound stillness unveils itself among the stars. We drift past ancient worlds, once vibrant with swirling storms and brilliant hues, now muted and quiet. These gas giants have become frozen husks, their tumultuous atmospheres stilled. A gentle hush seems to cover their vast expanse, as though the universe has pressed pause on their grandeur. Faint glimmers of distant starlight play across the pale surfaces of these distant spheres, revealing wisps of clouds grown thin and crystalline. In this serene tableau of space, the giant planets linger as silent witnesses to time. In that vast stillness, one might think the giants are simply gone. But absence of sound does not mean emptiness. These silent planets hold memories deep within their frozen skies. Storms have long since calmed, their thunderous voices reduced to a faint whisper in eternity. What remains is a gentle, almost reverent quiet, as if the cosmos itself is listening to the soft breath of these sleeping worlds. Under the soft glow of distant starlight, the darkness feels gentle, like velvet wrapping around memories of long-ago storms. The silence around them is deep, yet comforting, as if all of space has settled to honor their rest. The silent majesty of these frozen worlds speaks to us of impermanence. On human timescales, planets seem eternal, but the cosmos tells a different story. Even giants born from stellar nurseries do not shine forever. Their birth, life, and eventual quiet decay remind us that everything in the universe has a season. As we watch their long decline, we learn to see impermanence not as loss, but as a natural rhythm of creation. Each frozen giant is a lesson in fragility on a cosmic scale. We are reminded that even the most massive planets are not immune to time's passage. The forces that once gave them life, nearby stars and swirling gases, will eventually fade. Even these colossal worlds can be undone by the slow grace of time. Their fading teaches us that the universe is both creative and delicate, capable of nurturing life, yet patient in quietly reclaiming it. In witnessing their silence, we understand the beauty of cycles, birth and death entwined in the fabric of space. We find comfort in understanding that change is the only constant, even among the stars. Imagine a star blooming into a red giant, expanding to swallow its inner planets. The gas giants, in a delicate dance at the edge of this storm, might feel an immense heat before the star settles back into a faint white dwarf. What awaits them then is a slow fade into cold. In the new darkness, their atmospheres will gradually condense, and their skies will harden into ice. Over unimaginably long periods, the universe, patient and immutable, will transform them from roaring giants into silent relics of their former glory. Not all giants need a sun to wander the cosmos. Some are cast adrift, lone travelers in the dark. These cold wanderers carry no starlight, relying only on the faint glow of residual heat. In the emptiness between the stars, they become celestial icebergs, their once breathing clouds frozen into stillness. Their silence in the void teaches us that even solitude cannot halt the gentle decay that governs all matter. As eons pass, even these nomads will cool and dim, a reminder that everything is subject to change. These stories of fading giants teach a profound truth. The universe, despite its immense scale, is not static. The planets that once seemed unshakable also follow the tides of change. Even now, countless other worlds may be quietly shifting beyond our sight, moving toward their own quiet ends. By listening to the lessons of these planets, we learn humility in the face of cosmic cycles. Their fates remind us that all structures, no matter how grand, are woven into the impermanent fabric of the universe. We find solace in knowing that even in the vast silence of space, nothing truly lasts forever. The vibrant bands and storms that once defined them are fading reminders of what once was. Yet, in that fading, we find perspective. Understanding the transient nature of these giants helps us treasure the present, knowing even the mightiest of celestial showdowns have their quiet moments. There is wisdom in knowing that every moment of grandeur will eventually give way to stillness. In their subtle decline, a cosmic patience is revealed to us. They remind us that patience in the universe can span epochs beyond our imagining. By studying the fate of these planets, we confront a simple fact: nothing truly lasts. Even the colourful storms and glowing halos that adorned them will one day be memories. As their light dims, the silence that settles in can feel eerie and beautiful all at once. The planet's story, from raging youth to fading twilight, is like a poem written in ice and gas. By observing their silence, we learn to find beauty in quiet endings. Their fading shows us that endings can be gentle, and in that gentleness there is something sacred. Each frozen giant is a teacher in cosmic fragility. It shows us that even massive worlds have lifetimes, reminding us to be grateful for our own brief moment under the sun. In their stillness, these giants become silent teachers. The quiet space around them offers room to reflect on the universe. We sit at the edge of their shadow, absorbing the lesson that even silence can speak volumes. It is as if the cosmos is inviting us to listen to the wisdom of the void. The silence of these giants is not empty. It is full of meaning waiting to be discovered. As we absorb these lessons from silence and stillness, our minds naturally drift to the beginning of their tale. From echoes of their end, we can almost hear the echoes of their creation. Each frozen giant once gathered its bones from a stellar cradle, and even in their quiet, those origins shimmer faintly. In their silence, a memory of fiery birth flickers. It is a gentle reminder that every end has roots that reach back to a fiery beginning. By turning our eyes and instruments to these dying worlds, we ensure their stories survive. Though their clouds may freeze and fade, in our memory they remain vivid and important. We carry their tales forward, weaving them into our understanding of the universe. In this way, even in their silence, the gas giants continue to speak, teaching us to find meaning in change and continuity in impermanence. Their legacy lives on in the lessons we take to heart, reminding us that the end of one story can become the beginning of another. Thus, they echo on, whispering truths we would do well to listen to. These worlds are chapters in the grand story of the cosmos, each with a beginning, middle, and an end. While we stand on our own small world, these cycles happen on scales far beyond our daily life. And yet, we share in that story. The atoms in our bodies were once part of stars and planets. In learning from the fading light of distant giants, we realize that though individual stories end, the substance of their existence flows into something new. Even in silence, they contribute to the ongoing melody of the universe. Once, ancient philosophers believed the night sky was unchanging. Today, we know the truth. The cosmos is alive with transformation. Galaxies swirl, stars flare and fade, and even giant planets move through phases of life. By accepting this, we find a new sense of wonder at each sighting of a fading world. Every glimpse of a dying planet is a reminder that we witness history in motion. In accepting change, we honor the deeper wisdom that nothing stays the same. Impermanence is everywhere, even in the smallest details of nature. On a quiet autumn day, leaves drift to the ground and allow new life to sprout in spring. The gas giants remind us of that same gentle truth on a cosmic stage. What seems unstoppable today will gently give way tomorrow. Nothing is lost in this transformation. Even in silence, new stories will begin. By embracing this cycle, we find peace in the grand choreography of existence. We ourselves are part of this grand impermanence. Our lives span just a moment on the cosmic clock, yet we feel the passage of time deeply. Watching a planet fade teaches us that even things far larger than ourselves have their lifetimes. We honor and remember what was, and look forward to what will be next. In this way, these giants become our teachers, helping us accept change and cherish the present. They encourage us to live fully in each moment, aware that all things change with time. These worlds are born from cosmic dust, each a product of the same forces that build stars and galaxies. In their infancy, they were brilliant with activity, roiling storms, seething heat, swirling rings of gas and ice. We can imagine the vibrant bands of their atmospheres in youth, streaked with colour under a newborn sun. Thunder might have cracked across their skies, lightning dancing in massive storms. In that early chapter, they pulsed with energy. Now, here in the frozen silence of their twilight, we can trace those echoes of creation. The faint bands in their skies are the ghostly patterns of that original dance. The frozen cloud bands are the ripples left from the surging storms of youth. Even the ice itself is composed of elements forged in the heart of their birth star and beyond. In this way, the planet's beginning still resonates in its end. Deep inside, the planet's core remains a relic of those early years. Rock and metal at the center were the seed around which the gas swirled. Even now, traces of minerals and gases carry the fingerprint of ancient events. By comparing the planet's makeup to the cosmic soup it came from, we see a direct link. It is as if the planet carries its birth certificate in its very chemistry. From the first, the composition of a gas giant carries cosmic history. Hydrogen and helium from the primordial nebula still make up the bulk of its being. Heavier elements, carbon, nitrogen, oxygen, sulfur, and the like, exist in trace amounts, souvenirs of the dust grains that once circled in its birthplace. In their atmosphere and core, these giants preserve the chemical signatures of ancient stars. What we see now is composed of the same material that shimmered in the stellar clouds of old, long before the planet had form. In this sense, they are living fossils of the galaxy. In its infancy, a newly formed gas giant glows with its own internal fire. For millions of years, it radiates more energy than it receives from its star. That heat is the memory of its violent birth, slowly leaking out into space. As it contracts under gravity, the planet pumps out light and warmth, a beacon in the young system. Only much later does it settle into the more passive phase we see today. Even now, billions of years later, the fading giants may still emanate a faint glow, invisible to our eyes, but detectable in the infrared. This gentle afterglow is a relic of the fire and fury that forged them. In that quiet light, we can read their autobiography from their very first chapter. It is a subtle but tangible echo of creation, whispering the story of their origin into the cosmic night. The moons of a gas giant add another chapter to its origin story. Many of these moons formed from the same disk of material, or were captured from elsewhere. They share in the chemical heritage of their parent, remnants of the same swirling birth environment. In their orbits, they carry pieces of the puzzle, linking the giant back to its birthplace. Even as the planet wanes, its family of moons still echoes the conditions of its youth. All this evidence shows an intimate link between these giants' birth and their decay. Studying their ice and gas is like reading the endnotes of a story that began in cosmic dust. Every ring pattern and every trace element is a clue pointing back to the stellar nursery. Their silent decline is deeply woven into the colourful history of their origin. In them, the beginning and end merge into a single cosmic thread. Even the planet's appearance carries echoes of its formation. Some of the great storm scars and cloud patterns might trace back to initial turbulence in the protoplanetary disk. The giant's tilt and spin reflect how it accreted matter and its early violent history. Perhaps a slight wobble in its orientation is a remnant of an ancient collision. Each subtle quirk of its rotation and tilt may have been set in the chaos of creation long ago. In a grand way, the death of a gas giant can also be part of creation. As its atmosphere leaks into space, it will seed the cosmos with its ingredients. Elements once locked inside the giant will eventually become part of new stars and planets. The ringed debris and frozen gases may one day be woven into fresh planetary nurseries. In that sense, each planet's end echoes the act of creation, renewing the cycle of cosmic life. We might think of these planets as ancient storytellers. In their slow demise, they impart wisdom not with a roar, but with a whisper. Their story was long and magnificent, and in its final pages they speak of patience, humility, and acceptance. Listening closely, we catch every lesson they offer in their waning light. They remind us that sometimes the quietest voices leave the deepest impression. By turning our eyes and instruments to these dying worlds, we ensure their stories survive. Though their clouds may freeze and fade, in our memory they remain vivid and important. We carry their tales forward, weaving them into our understanding of the universe. In this way, even in their silence, the gas giants continue to speak, teaching us to find meaning in change and continuity in impermanence. Their legacy lives on in the lessons we take to heart, reminding us that the end of one story can become the beginning of another. Thus they echo on, whispering truths we would do well to listen to. These worlds are chapters in the grand story of the cosmos, each with a beginning, middle, and an end. While we stand on our own small world, these cycles happen on scales far beyond our daily life. And yet, we share in that story. The atoms in our bodies were once part of stars and planets. In learning from the fading light of distant giants, we realize that though individual stories end, the substance of their existence flows into something new. Even in silence, they contribute to the ongoing melody of the universe. Once, ancient philosophers believed the night sky was unchanging. Today, we know the truth. The cosmos is alive with transformation. Galaxies swirl, stars flare and fade, and even giant planets move through phases of life. By accepting this, we find a new sense of wonder at each sighting of a fading world. Every glimpse of a dying planet is a reminder that we witness history in motion. In accepting change, we honor the deeper wisdom that nothing stays the same. Impermanence is everywhere, even in the smallest details of nature. On a quiet autumn day, leaves drift to the ground and allow new life to sprout in spring. The gas giants remind us of that same gentle truth on a cosmic stage. What seems unstoppable today will gently give way tomorrow. Nothing is lost in this transformation. Even in silence, new stories will begin. By embracing this cycle, we find peace in the grand choreography of existence. We ourselves are part of this grand impermanence. Our lives span just a moment on the cosmic clock, yet we feel the passage of time deeply. Watching a planet fade teaches us that even things far larger than ourselves have their lifetimes. We honor and remember what was, and look forward to what will be next. In this way, these giants become our teachers, helping us accept change and cherish the present. They encourage us to live fully in each moment, aware that all things change with time. From our human perspective, a gas giant's life is nearly infinite. To them, a millennium passes like the turn of a page. One of our generations is barely a whisper in their long story. We live our lives in a rush, but in the planet's patience, there is no hurry at all. They might outlast whole epochs of human history while we barely notice. We measure our lives in years, the planet in millennia. The things we build, cities, stories, our very selves, grow and fade far faster than these ancient worlds. For the giant, even the longest human lifetime is like a blink of an eye, barely registering in its quiet span. Its survival through unimaginable time reminds us how fragile our own existence is. In comparison, our greatest achievements are but a brief ripple on the ocean of time. This perspective can be humbling, but also profoundly freeing. In the eyes of the universe, our worries are small. Day-to-day struggles seem trivial when set against the great patience of the cosmos. And yet, this realization can be comforting. Our fleeting lives become more precious when we understand their rarity. Knowing we are part of this vast story can bring a quiet joy. The giant's patience can even teach us lessons. We rush through our days as if time is scarce, while they remind us there is plenty. Their quiet persistence shows how to savor the moment rather than hurry. Perhaps in their steadiness, we find guidance to live more fully. They endure calmly. We can learn to pause in their presence. This gentle wisdom is a gift from worlds that have known time longer than we have dreamed. In this light, every moment of our lives glimmers with significance. Though our years are fleeting, they are all we have, and we may choose to cherish them. The planet's grandeur reminds us how extraordinary it is to be alive at all. We may be small and brief, but we are conscious. We can appreciate this vast universe. Our very awareness links us to the giants, giving meaning to our place in the universe. Knowing this, we can find solace in the silence and strength in the stillness. Even now, our curiosity draws us to these distant worlds. Telescopes and spacecraft carry our questions to the giants, seeking kinship across space. In starry nights and quiet skies, people have always looked up, finding comfort in the cosmos. We stargaze and wonder, and in doing so, we honor the patience of those silent worlds. Through our eyes, even the quietest planet finds a listener. In our stories and science, we carry their memory beyond their silence. Our fleeting nature can also inspire gratitude and responsibility. If a human life is brief, then each day is incredibly valuable. We may feel small, but that means we should cherish our time and the tiny corner of the universe we call home. This sense of urgency can motivate us to protect our planet and each other. In learning from the planet's patience, we find a reason to cultivate care in the time we have. Their quiet example humbles us, pushing us to live with purpose. Major struggles that seem colossal to us appear small in the cosmic frame. conflicts and worries that occupy our minds may seem trivial on a galactic timescale. Perhaps this cosmic perspective can calm our anxieties. What feels urgent now might fade in 1,000 years. It's not to diminish our problems, but to remind us of our resilience and capacity for growth over time. Even our greatest challenges can become part of a larger story, one we continue to write with each day. Just as the planets fade, someday our world will change beyond recognition. Our sun will not burn forever, and Earth itself will meet its end. Yet knowing this can enrich how we live now. Understanding that nothing lasts forever helps us see the beauty in the present. The dance of life and death is universal. We are participants, not outsiders. In this cosmic context, even the briefest life shines brightly. When we consider our own mortality, the giants remind us to find peace. Life may end, but it can be rich up until then. Our fears of an end are natural, but they also highlight how precious life is. The ancient giants have faced endings and continued to exist in memory. We too can face ours with grace. We might be brief, but we have all the time we need to make our years meaningful. There is courage in embracing each day wholeheartedly. The giants also remind us of the importance of compassion. Human conflicts might seem petty to an immortal planet, but they matter to us. Perhaps knowing our shared smallness can unite rather than divide us. If this vast universe is watching, there is no room for lasting hatred. We share only a brief moment in time, a chance to care for one another. In cosmic terms, kindness is a gesture that echoes far beyond our years. In a way, each of us is the universe perceiving itself. Every thought and feeling we have is a tiny reflection of the cosmos's wonder. When we look up at the stars, we are also looking at ourselves. This perspective reminds us that the universe is not only matter and time, but also consciousness. We bring a spark of awareness to these distant giants, and in doing so, connect to their silent existence. In our tiny awareness, the cosmos lives and knows its own story. Understanding the giants teaches us about ourselves. By seeing our fleeting moments in their context, we gain wisdom about how to live. We might think our lives are inconsequential, but in cosmic terms, each life adds beauty to the universe. Every act of kindness and every moment of curiosity resonates across time. In embracing our fragility, we realize we are integral to the universe's story. Even tiny lives like ours are meaningful threads in the cosmic tapestry. In the grand scheme, we might be small and brief, but that does not mean we are insignificant. Our ability to appreciate beauty, to love, to create, is something no silent planet can fully grasp. The giant's quiet patience is powerful, but it is made all the more meaningful by our presence. We become part of their story simply by living, by looking up, by wondering. Even if our time is limited, our capacity to cherish each moment is boundless. In that realization, we find our place among the stars. With this sense of perspective, we continue forward. Each day becomes a gift to be savored. We may be tiny and our time short, but we walk under the same sky as those silent giants. In our own way, we too hold the universe's patience within us. And so, with gratitude and wonder, we go on. With humble hearts and curious minds, we continue our exploration of the universe. The giants remain in our thoughts as we look ahead. This perspective of humility and wonder stays with us, guiding each step beyond. In quiet reflection, we carry their lessons forward. Finally, we are reminded to be gentle with ourselves. In the grand tapestry of time, each life is a thread of beauty, no matter how short. We live, we love, we wonder, and that is enough. The giant's patience teaches us that there is time for everything important. If nothing is truly lost, then our own moments become part of something larger. So as we gaze up at the stars each night, we remember that we carry those giants' quiet wisdom within our hearts. Their ancient patience now lives in us, guiding our steps. With that gentle understanding, we embrace our fleeting journey, knowing we are part of the eternal. In the vast stillness of space, our brief lives are not insignificant. They are notes in the eternal melody. We carry this calm understanding forward, not as a conclusion, but as a new beginning. Each day is a journey to be lived fully, as our story continues to unfold. With the giant's wisdom within us, we step quietly into the next chapter of our cosmic adventure. Our perspective is forever expanded, and still we go on. With humble hearts and curious minds, we continue our exploration of the universe. The giants remain in our thoughts as we look ahead. This perspective of humility and wonder stays with us, guiding each step beyond. In quiet reflection, we carry their lessons forward. In the midst of our busy lives, this calm understanding becomes our companion. Each ordinary day holds a bit of the extraordinary when seen through the eyes of the cosmos. We may walk on Earth for only a short time, but in that time we become part of something eternal. In the giant's silence, we find inspiration to be present, to be gentle, to be aware. We carry the quiet wisdom of the gas giants in our souls. And so, with gratitude and wonder, we go on.